What is up, everyone? Welcome back. We are here with Organic Chemistry 2 Exam 2 review. Gonna start off by saying that I get a lot of complaints that I yap too much in the beginning, so I'm just gonna not yap anymore. I don't know why it's an issue, because you can just skip until I start the actual OChem stuff, but it's whatever. Y'all look, you hurt my feelings, so I'm not gonna yap. I do want to say though that this exam was my favorite exam, and it was the highest scoring exam for all of OChem 1 and 2, including the finals. And so I really had a lot of fun with it because it's super repetitive in my opinion. It's not even an opinion, it's just a fact. It's just repetitive, right? Especially Diels-Alder and aromatics. There's only so much you can do with them. So once you've done enough of it, it doesn't matter what they throw at you, you already know how to do it, right? It's kind of like SN1, SN2. When we first learned that stuff, it was super chaotic. But then at some point, once we fully understood SN and E, it didn't matter what we were asked. We just knew how to do them. So this is kind of like that, right? In my opinion. And just to give you an idea of how much fun I had with this, during one of my I'm yapping again, but I'll keep it short though. During one of my clinicals for as an EMT, it was the ambulance shift, I was chilling in the firehouse station thing, and everyone was asleep, all the paramedics and firemen and all that, and I was super bored because nothing was going on. And so I just pulled out my little notepad and I just spammed every single reaction I knew, and I built some crazy carcinogen or something, and it was fun because I just remembered everything, right? I didn't have to look at anything, just remembered all of them and could just go crazy with it. So I hope y'all feel the same way about this exam afterwards. But without further ado, let's begin. So we're gonna start with ether and epoxide reactions. This stuff is pretty much OChem 1. So you've seen all of these before and they're being reintroduced. A common question I get asked is, do we have to remember everything from OChem 1? Because I just keep seeing them come up and you keep saying that we don't have to know them. This is my answer. You don't have to know everything from OChem 1. Obviously, remember your fundamentals, right? Nucleophiles and electrophiles, just remember that concept. For that reason, I would say just remember how SN2 and stuff works, just because that's a very fundamental reaction that you'll see in a lot of other types of reactions, okay? But as far as the other things alkene, alkyne, alcohol synthesis reactions, this is what I'll say. You only need to know OChem 1 reactions if they reintroduce it. So you don't have to know every single reaction, but if it's shown in your slides or your teacher talks about it, then you should know it. Okay, that's what I'll tell you. So let's go ahead and start with this. The first reaction for ethers is going to be Williamson ether synthesis. Now, this name I really don't care about, but I'm just bringing it up so you can locate it in your slides. But Williamson ether is pure SN2. So the reagent would be an alkoxide, and you react with an alkyl halide. So we'll do that. And this is SN2, right? You attack carbon and kick off this leaving group, and you end up with this diethyl ether. Okay? Don't have to explain much, right? SN2. Don't forget, this is an ether right here. It's an oxygen bonded to two R groups. And the R groups, right, the atoms that are directly connected to the O have to be carbons. After that, you can have whatever you want. But you have to have two carbons bonded to the O to have an ether. Otherwise, you get different functional groups. For example, if one of your R groups was an H, now it's an alcohol. If both of them are H, that's a water. So it has to be carbons. Don't mix this up with esters. We shouldn't be mixing this up at this point. But an ester with an S is going to be a carboxylic acid derivative where it has a carbonyl group. But an ether is going to be just ROR. Okay, so that is one way you can see this. Maybe, let's say we have a neutral alcohol. Neutral alcohols are weak nucleophiles, so maybe they can react with your alkyl halide, but it's not ideal. So we can make it into a strong nucleophile, right? Reacting with a strong base. Usually we see NaH or just H-. But I have seen neutral sodium and neutral potassium, so just know about those. But they're all going to do the same thing effectively, right? Just make a negative oxygen, electron rich, strong nucleophile, and then you can react with whatever you want. So we'll do methyl bromide. So attack this carbon, kick that off, and you end up with ethyl methyl ether. Pretty chill. Okay. Something minor to mention is usually you're going to react with primary alkyl halides for Williamson ether synthesis, because after primary you risk elimination occurring, because remember, this is a strong nucleophile, strong base. So if you want to guarantee that you get a substitution product or that you form the ether, you're going to see primary alkyl halides. It can still work with secondary, but just usually primary. And because of that, stereochemistry is not an issue ever, if it's primary at least. Okay, let's do a backwards version of this. If we were provided this molecule and we were asked, how did you make this? Then a couple ways to think about it, right? This oxygen is the one that attacked, okay? So that means that the oxygen could have come from this ethane and attacked a molecule like a benzyl bromide, or the oxygen could have come from the benzene and attacked something with an ethyl group on it. So both of those could be correct. Maybe both of those are not correct, or maybe one of them is correct. So you can try both of them out, right? Let's try both options. The first one would be where the oxygen came from the benzene and we're reacting with an ethane that had some halogen on it, like that, right? The second option would be to put the halogen on the benzene. So we'll put an iodine here, and the attacking oxygen came from the ethane. Take a quick moment to answer this question. 5, 4, 3, 1. The answer is, it is just the first one, okay? The first one, same thing that we've been doing for the past 5 minutes. Your O is negative. It's going to attack this primary alkyl halide, kick that off, and you end up with your product. The issue with the bottom one is that in order for this to work, your oxygen would be attacking an sp2 carbon. If you remember anything from OChem 1 or even like everything up until now, you just don't attack benzenes or sp2 carbons like that, right? With like with a nucleophile, that's not how it works. So this is going to lead to a no reaction. So that means that our answer would just be this, okay? This is how we make that product in green. So definitely keep this in mind, right? I know now you're learning about benzene reactions and how to attach things or break benzenes and all that stuff. But don't forget that your original reactions that you've learned, none of those do anything to benzenes or sp2 carbons or anything like that, okay? If you want to attack a benzene, you've learned now, or I don't know what when you're watching this video, but you've learned that you need like catalysts and like some wacky reagents that you've never heard of before in order for those to occur. So if it's an old reagent, then just forget benzenes. Like just don't do anything with them. Okay. So SN2 can only attack just like the primary and secondary carbon. So keep this and you'll be good. Let's move on. The next reaction is going to be, it's called alkoxymercuration demercuration, right? Alkoxymercuration demercuration. Now this is also an OChem 1 reaction, but the emphasis was on oxymercuration demercuration for OChem 1. I'll show you what it means. You did learn this one as well, the alkoxy, but it isn't focused too much. So it's this one right here, right? HDOAC2, THF, and H2O, okay? NaBH4. So y'all learn that this is a Markovnikov addition of alcohols, right? Of an OH. And so your answer would be that, right? You add to the double bond and you end up with no double bond and you have your OH attached. Now, if you want to add an OR group instead, right, like an OR group, then you just alter this thing right here. You're going to turn this into an alcohol. So ROH would give you this product. So it's the same thing as oxymercuration demercuration, except instead of adding an alcohol, you're adding an alkoxy group. Does that make sense? Because the way it worked was when you did H2O, initially you added the entire H2O. So you added OH2. Of course, your oxygen is plus. So through a workup step, you get rid of one of the H's and you end up with a neutral alcohol. But when you're trying to add an alcohol to it, ROH, then this time you're adding the alcohol. And it's positively charged. So through a workup step, you deprotonate it and you end up with this, right? Your H is gone. Now you have the OR group. Now this is an ether, right? Because R can be anything, right? Like if we had this, let's say we did ethanol, then we'd end up with this, right? This part is the ether. So yeah, that's like another way to form the an ether. And I guess something I want to mention, don't forget this. I don't know how deep it is, but don't forget it, because if you keep it, then you're still gonna have an HGOAC attached, and like, come on, bro, you don't want that. So yeah, something small. Cool. Let's move on. I don't know what this reaction is called, so I'm gonna call it the 2-alcohol reaction. It's literally what it sounds like. You're gonna have 2 alcohols. You're gonna have, so H2SO4 or just like H plus, you have this and then you end up with that plus H2O. Okay, I'm added this plus H2O. I usually like never include side products or byproducts, but I included it just to like show you something. Essentially, the OH of one of these and the H of another one are going to leave as water, and then you merge the other two things, right? So you merge this with that. That is the simplified version of this. I'm not going to get into the whole mechanism and stuff, but that's all it is. So if I gave you this alcohol plus that, what would your answer be? Let me change this color. Just choose one of them to keep the same. I'll choose the blue one just because it's simple in my opinion. So keep that. You have one oxygen already, so add everything else that's not oxygen from the red. So just add these, like the red carbons, right? So that would be that, and that's your answer. Okay, by the way, under acidic conditions. That's all it is. And as you can see, this is an ether. This reaction also usually occurs with primary alcohols. So this might not be the best thing, but like it's still possible. But just keep in mind, usually primary alcohols, because the issue is when you have secondary and tertiary alcohols and you have this strong acid, you also risk elimination again. But I don't want to confuse you all, so I'm just gonna forget I said anything. But in case somebody's like a try-hard organic chemist and's like, you're wrong, I'm just addressing that concern. But ignore what I said, okay? Whatever I said was correct. That reaction works as I showed you, perfectly fine. Okay, if you might make a connection here. There was this reaction that you learned last exam. This was the esterification, right? Fischer esterification. I don't remember what I taught anyone, but like you just do the same thing, right? You keep one thing the same and then you attach the R group of the other thing. So you would end up with this, and then you add that R group, which is the ethyl. So it's the exact same thing, except you don't have this carbonyl there. Okay, let's move on. Next, we're going to do stuff with HBr and HI, probably HCl as well, but usually we see HBr and HI. So let's go ahead and draw some stuff. Okay, cool. If we're reacting this with hydrogen iodide, what is going to happen here? Well, keep in mind, this is a strong acid, so it dissociates into H plus and I minus. Okay, the first thing that's going to happen, please lock in and pay attention. The first thing that happens, the oxygen is going to act as a base and it's going to accept this proton. Okay, when you do that, your intermediate will look like this, where your oxygen is positive because it has too many bonds. Now, a lot of people think that water is the only leaving group that has like a oxygen, right? If it's not water, if it's something else, then it's not a leaving group. No, okay? If your oxygen has a positive charge, it can be a leaving group. It doesn't matter if it's water or an alcohol or whatever. If it has a positive charge, it can be a leaving group, because the whole thing that's going on is that oxygen has too many bonds, and so it wants to lose a bond, which is why it leaves, okay? Hence, leaving group. So don't think it has to be just water. Over here, what do we have? This is an alcohol, and it is, in fact, a leaving group, because as I mentioned, it has too many bonds, okay? So now we have our iodide ion, okay? Let's bring this iodide ion over here. This iodide ion is going to do an SN2 attack. It's going to attack one of these carbons, okay? Because the oxygen is trying to break off from one of these carbons that it's bonded to. Now, clearly, it's not going to be this one right here, because that would that would involve attacking an sp2 carbon. So it's going to attack this carbon right here, okay? And when it attacks this carbon, we're going to break this off. And what do we end up with? This is our answer. Okay, so we can number this 1, 2, 3. We got 1, 2, 3, and our iodine attached. And as you can see, now we have a neutral alcohol. At first, it was positively charged, but once it left / broke off, now it's neutral. So it's good, right? We're chilling. Same thing would happen with HBr, except you'd attach a bromine, okay? Let's do another question. Okay. If we were to react this with HBr, what do we do? The first step, as I always say, right? Anytime you have an acid, just see where the proton goes. That proton must have a purpose. So see where the proton goes. It's the same thing over here though, but the oxygen will take the H and it's gonna become OH plus, okay? Now our bromine is here and we're fighting between this and this position. Both of those are acceptable because they're sp3 carbons. Here is where we add one more factor to consider. So when this oxygen has a positive charge, that makes it want to break a bond, right? Which means that it's very electronegative, or it's very partially negative because it wants to take electrons, which means that both of these carbons are partial positive, okay? Now that doesn't help us. We want to know which one is more partial positive. To figure this out, you just look at which carbon would hold a positive charge better. So just pretend we had a carbocation here and a carbocation right here. Which one would survive better as a carbocation? It would be this top one, because this is going to be primary but resonance stabilized, right? Whereas this one is just primary. So this is going to be the better option. It is going to be the more partial positive carbon. The other one is just partial positive. Now, some people think, why is it partial positive if you're donating electron density? Wouldn't that like neutralize it because you're donating negative stuff? Do not think of it like that, okay? When we talk about electron donating or electron withdrawing or any inductive effects, okay, let's take electron donating, for example. We're not literally donating negative charges to neutralize this, and now it's just zero charge. That's not how it works, okay? It's a way to think about it, right? You can think of it like I'm donating negative charge so that it becomes neutral, but you're not literally doing that, okay? All it's doing is it's stabilizing it. So the more substituted carbon or the resonance stabilized carbon is still going to be super partial positive, but it's going to be stabilized, if that makes sense. So you take the partial positive, the most partially positive carbon of the two, and you're going to attack it, right? So the bromine will come attack this one, and you break this off. And what do you end up with? Okay, that is it. Now, I do want to mention that if they say that this HBr is in excess, that means you have to consider the possibility of another reaction occurring. So let's go ahead and do that. If we had HBr in excess, we just say there's HBr again. What can you do here? Well, I see an oxygen, and the oxygen definitely has some lone pairs, and this HBr is actually H plus and Br minus, and what we know is that oxygen can bond to the H. So what do we get as our little intermediate thing? This time we made our oxygen into a water, and water is a tough leaving group. And we saw Br minus, so you're going to attack this and kick that off. And you ultimately end up with 2 bromines attached. So it's interesting, right? Because our previous example, we had 1 alcohol and 1 halogen. This time, we have 2 halogens and no alcohols. So the reason for this, obviously, is because the oxygen was not a phenol oxygen. Okay, phenol means it comes directly off of the benzene. The oxygen that I circled here is just, a regular oxygen. It's not part of a benzene, which means that you're going to have something like this occur. Now, if they don't mention excess, I would still go ahead and react all the way, because if they don't write excess, it is assumed that it is an excess. The only time I would tell you to stop at this product right here is if they said 1 equivalent of HBr. But if they do not say anything, or if they say excess, then go all the way through. Okay? So once again, let me just write it one more time. If you understood this, then just skip this. But I want to keep it nice and clean. The first step, right? Let's do HI this time. The oxygen will accept the proton and become OH plus. Then we are going to take a look at this carbon because it's most stabilized if it was a positive charge, and the iodine will attack this one and break that off. Okay, and when that happens, we have 1, 2, and carbon 3. We're going to get this carbon 1 bonded to in iodine. Then we have carbon 2, carbon 3, right? Carbon 2, carbon 3, OH. This is what we have initially, but then we have more HI floating around. So since we have more HI floating around, our oxygen is going to take the H again, and it's going to form a water molecule that's positively charged because it's still bonded to something else. Okay, then our iodide ion will come in and attack the carbon, the primary, and kick this off. And ultimately, we would end up with a product that has 2 iodines attached. Okay, so that is the final answer. Definitely remember this. I've seen it on last year's exam, and so it's important to know the differences between the 2 types that I showed you right now. All right, let's move on. About to show you something new. Probably not the most likely thing to show up, but I mean, I've seen it. I don't know if it was a quiz or something. Someone sent me the question, so I'm assuming it's a recent thing. Protecting groups. Protecting groups are more apparent after this exam and potentially on your MCAT. So protecting groups, the concept is that you're trying to protect a group because you're not wanting it to react. So let me give you an example. Let's say that we are trying to react this with, I don't know why I keep using ethyl, but it's pretty simple. If we're trying to react this with a Grignard reagent, we're essentially looking at this thing, okay, this negatively charged carbon, and our intentions are to attack this and attach a carbon, form an alcohol, and whatever. But you have to remember that on top of this being a nucleophile, it's also a very strong base. And so instead of it reacting with our desired reactant, you're actually going to get this as your product. And no reactions occurring. That's all that happens, right? So how do we attack this carbonyl without reacting with this alcohol that's in the way? This is where protecting groups come in. So you're going to do something to cover this up while still keeping it on the molecule, but you're going to cover it up. Then you're going to react with this thing, do whatever, and then uncover this. Okay, so I'll show you something that they taught you this in the slides. It's called TIPS CL. It stands for triisopropyl silane. So let me just keep this here. Okay, TIPS. I'll put in parentheses, but let me actually draw it out for you. So it's silicone with 3 isopropyls and then like a chlorine. It's kind of like tosyl chloride essentially, right? But you might also see it like this. This is isopropyl and there's 3 of them, and then the silicone, right? So when you react it with TIPS chloride, as I mentioned, it's like tosylation. You form this thing right here. So I'll just say IPR, and isopropyl, right? So this thing is protected now. The oxygen is protected. So when you bring in your Grignard reagent, it's going to do what you want it to do, where it's going to attack this carbonyl, and you'll end up, pretend we have a workup, it's going to do that. Okay? By the way, you might sometimes see this solvent, okay? But the main reagent is this thing, the TIPS chloride. Okay, so now after you do this, you want to go back to your alcohol over here. You want to get rid of the protecting group because you're done doing whatever you need to do. So then you're going to react with something called TBAF. Okay, it's tetrabutylamine fluoride or something like that. So TBAF, another way, like the actual formula is this. Butane, there's 4 butyls, and it's this right here, right? You also will see like H2O. Why did I put a parentheses? So this is the actual TBAF thing, right? The tetrabutyl amino fluoride. Sorry, I don't know what it's called. Something like that. Yeah, so you get that, and you essentially remove that protecting group, and you go back to your alcohol. So this is your answer. Okay, so just keep this in mind because I worked out the whole steps, right? But if they just straight up gave you a question that's like, step 1 is TIPS CL, step 2 is Grignard, step 3 is the protonation step workup thing, and then step 4 is TBAF, people go crazy. They don't know what's going on. Like, what is all this stuff? I just showed you how it works, right? TIPS is going to be a protecting group, and then you're going to attack your carbonyl or whatever it is with your magnesium chloride, your Grignard, and then you're going to deprotect. So keep that in mind, okay? I'll leave it at this for now for protecting groups because I think that's the only one you need to know. All right, let's talk about epoxides now. So quick refresher on how to form epoxides. You're going to use a peroxy acid, or sometimes I see it written as per acid. A peroxy acid, the general formula is RCO3H. Okay? What does that look like? It looks like this. It's a carboxylic acid, but you have this extra O bond. Okay? So the 3 oxygens is important. The most common one that everyone knows and loves is MCPBA, which, as a refresher, actually, let's talk about it. It stands for metachloroperoxybenzoic acid. So it's a peroxybenzoic acid. It's a benzene that has a peroxy acid, and it's metachloro. I'm purposely bringing this up because you're learning about aromatics. Metachloro means that the chlorine is meta to it, right? So this is ortho, this is meta, and this is para. So the chlorine is on the meta position, which means that it's right here. Okay? But essentially this whole thing is an R group, and this is the main part that we're looking for, right? The thing that I rectangled. It's a peroxy acid, so it does what we need it to do, which is form epoxides. Okay? So let's write it out. RCO3H or MCPBA. That is going to give us our epoxide, right? We know this from OChem 1, so don't need to talk much about it. But I do want to mention something that not everyone knows. Let's say they gave you this right here, and they said MCPBA 1 equivalent. What would your answer be? I'll give you 2 seconds. 2, 1. Okay, your answer is going to be the right side. So you'd end up with this. Now the reason for this, okay, I'm not going to get into the mechanism of this because it's in one of my previous videos, but essentially when you have alkene reactions, your alkene is acting like a nucleophile. It's using its electrons to bond to things, okay? So it has to be what? It has to be electron rich if it wants to act like a nucleophile and use its electrons to bond to things. So if you are reacting with 1 equivalent of MCPBA, the one that reacts is the more activated one, or the more electron-rich double bond. So what is this? It's an electron donating group, right? This double bond has more electron donating groups than this double bond. And you're donating electrons, right? You're donating electrons, which means that this double bond has more electrons, right? It's more electron-rich than the left double bond. So the right one is more activated, it's more likely to react, and it's going to react like as a major product. So definitely, I want y'all to know this, that the more substituted your double bond is, it's going to be more reactive. Now, some people, think about stability as being, the opposite of reactivity. Just ignore that, okay? This double bond is the most stable, but for a different reason, different topic, just ignore that. It is the most reactive of the 2 double bonds because it has more electron donating groups, okay? Let's talk about another way to form epoxides. I'll just leave this here. It's actually an interesting one. Somebody brought this up to me last semester, and I was like, that's pretty cool. But I was like, I don't know if it's real, but it actually is real. So I'll show you what it is. So let's say you have a double bond. We're going to use the reagent Br2H2O. Low likelihood of showing up, but just remember what it does, okay? This will give you Br and OH, right? This is called a halohydrin. You have a halo and a hydrin, so halohydrin. Hopefully you can anticipate what I'm about to do. But you have this, and what can you do here? Deprotonate the alcohol, right? You can use that, or you can use just a regular negative OH. That is going to give you O minus. Let's put it on the other side. O minus. And we have an oxygen that's negative, and we have an alkyl halide. So it's going to be like an intramolecular, like SN2. So it's going to attack this. But as you can see, right, carbon 1, carbon 2, oxygen, that's going to form an epoxide. So we'll get like this right here. So it's pretty interesting. I'm glad someone brought it up like in the past, because it shows that y'all be thinking. So yeah, definitely know this. Also another example of something that's not likely to show up, but still remember it, okay? Sounds good. Let's get rid of this. Trying to think what comes next. I guess on the topic of epoxides, we can talk about epoxide opening. This is actually a very important thing to know. Epoxide opening. Let's go ahead and... Oh, by the way, nomenclature. In case you're curious. If you're not curious, skip this part. But this molecule is called propene oxide. People wonder, why is it ene oxide instead of propane? I don't see any double bonds. Because you name it after the double bond that it came from. So this was a propene, and then you turned it into the epoxide. So you just keep that base name as the thing it came from, propene, and you get oxide. So that's what it is. Okay, so this is a propene oxide. There's 2 things we can do. Okay, we can react in acidic conditions or under basic conditions, and we'll get 2 different products. So for acidic, we're gonna go ahead and use CH3OH, okay? And to indicate that it's acidic, we're gonna have the H+, right? If you see H+, it's acidic. If you don't see H+, or you see like OH-, it's basic. But if you see H+, it's acidic. So we'll do this. For basic, we'll do CH3O minus. Okay. And another thing, you might, you know what, I'll come back to that later. So let's go with this, right? For acidic, I want you to, I'll tell you should I tell you the shortcut or the mechanism? I don't know. I'm not going to tell you the shortcut until the end. Yeah, I'm just not going to tell you. Okay, for acidic, what's going to happen? Remember what I said about protons? If you see a proton, do something with it, okay? The first step will be do something with it. The first step is this. You have H+, oxygen will take it, and you're going to get this. Okay, remember what I said. Oxygen has too many bonds. Oxygen has a plus charge. It doesn't like having too many bonds. It doesn't like having a plus charge. It wants to be either neutral or negative. Therefore, the oxygen has a partial negative charge, and the adjacent carbons have partial positive charges. Okay, because it's pulling on both of those carbons bonds, so it can steal it entirely. But it can't do it to both, obviously, right? It can only do one because it can't lose two bonds. But then what is the more partial positive carbon? It's the one that's more substituted because it can be more stabilizing to that positive charge if it were to have one. So that's going to be this carbon right here, right? This is the more partial positive carbon. So that is our true electrophile of this molecule. Then we bring in our nucleophile. So CH3OH, right? It doesn't matter if it's weak or strong. We're under acidic conditions and we establish our electrophile. So we're going to attack the electrophile and we're going to break this bond off. And so our product would be this, where we have our alcohol up here and we have our OCH3 here. And of course, right, it's with the hydrogen, but then like through workup, you just remove it. So I'm just disregarding that hydrogen, but you end up with this. Now, we're not entirely done yet. This molecule in particular does not have stereochemistry on this carbon, but let's pretend that it is chiral. We have to know how the stereochemistry works. This is what you'd get. Okay? So this is our product of the acidic conditions. We have we have anti-addition, and we attack the more subposition. Okay, that's for acidic. Now for basic, it's semi-opposite. Okay, I'll tell you what the opposite part is after I show you. So we'll go ahead with this, right? We don't have any protons present, so this is what we're dealing with, just the same thing that we started with. Now, of course, oxygen is still partial negative, and these are still partial positive, but the effect is not nearly as pronounced as it was previously. Because what? Oxygen is neutral now, so it doesn't need to pull strongly on these bonds and break it off. Otherwise, it's going to become O negative, and it doesn't need to do that because it's already neutral. Okay? So that means that when we have a nucleophile, we aren't looking at what's the most carbocation like carbon. That's not important enough. Instead, we look at what's the easiest to access. Okay, so essentially, where is it the least sterically hindered? It's going to be the less substituted carbon. So you're going to attack the less substituted carbon under basic conditions. Once again, it does not matter if it's strong or weak nucleophile. If it's basic conditions, just attack the least substituted side. So you attack that, and you break this off. And what is our product? Let's do stereochemistry. Okay, so what do we have here? We have anti yet again, but this time we attacked on the less substituted position. So what remains the same? The anti aspect of it, right? They're both going to be anti. The difference between acidic and basic is where you attack. Acidic attacks the more substituted position, and basic attacks the least substituted position. Now, why does this work? It's just like geometry, bro. Like this is facing one direction, you can't really attack it from that direction because there's a lot of stuff going on. So you're gonna attack it from the back. Like, that's all I can really tell you. You're just attacking it from the backside attack. I don't want you to confuse acidic with SN1 and basic with SN2. Okay, acidic is like SN1 in the sense that you attack the most substituted position, but it's different in the sense that you 100% attack from the back and you 100% end up with anti-addition. Okay. This one is a lot like SN2, where you do a backside attack and you attack the least substituted position. So if you want, you can think of basic like SN2, but acidic is not entirely like SN1 because of the stereochemistry aspect. Okay, so definitely know this. This is like a higher yield question that they could ask you when it comes to ethers and epoxides. Another reagent we can use is a Grignard reagent. So usually we see Grignard reagents with carbonyls, but you can use it for this as well. And as you can see, I just gave you the Grignard reagent, which means that it's under basic conditions because I didn't specify that there's H pluses. So it's basic, right? So we're going to attack the, fill in the blank, less substituted side. And we end up with that right there. All right. Let's move on. I guess here, sorry, let me clarify something. You're probably wondering, how can you see a weak nucleophile under basic conditions? Like, literally, if they gave you this, CH3OH, CH3O minus, this is a weak nucleophile under basic conditions. That's what it is. Okay. So for the 57th time, if you do not see an H plus present, if you don't see this guy at all, it's basic. Okay. I don't care if it's a weak or strong or mediocre or whatever nucleophile. If you don't see the H plus, it's basic or neutral or something, which does the same thing. If you see the H plus, it's acidic. Just please remember this. All right, let's move on. Make sure I didn't miss anything. I think, yeah, that's going to be it for ethers and epoxides. So now we're going to move on to conjugated systems. I don't really have much to say on conjugated systems because it's like a precursor to Diels-Alder, but there are a couple of things I want to mention. So the first is kinetic versus thermodynamic products. Very important thing to know. Okay, so let's talk about like an example. Well, I'll give like a very basic example and then I can follow it up with some more stuff, right? So if I take this and I react it with HBr, if you remember this, it's like an alkene reaction from OChem 1. What you would do is you have H plus and Br minus, and your double bond is going to bond to the H. One of the carbons will use the pi electrons to bond to the H. The other one will become a carbocation. So we always like remember that the one that is most stable as a carbocation will become the carbocation. So like this would bond to the H, and this would become the carbocation, right? So you would get this. And then the Br would attach to there, right? You would end up with that. Okay. However, this reaction also has a second product. The second product is this. Or like second type of product. So I'm gonna put them down here. So we got this one, and we have this one. Okay. This right here is called the 1,2 product because the H was attached here and the Br was attached here, right? That's 1 and 2. Over here, the H attached over here and the Br attached over here. This is called a 1,4 product. Just some terminology stuff, but you don't have to know that. So the question is, when do we get the 1,2 product? When do we get the 1,4 product? Because they do come from the same molecule. I want you to think of it like this. What was the intermediate? Let me erase this. What was the intermediate again? The intermediate was this. And you might be thinking that doesn't match up. That doesn't match up with this thing down here. It actually does after you resonate, right? So if you resonate this, double bond goes over here and you're positive right there, right? As you can see, it matches up with that. But here's the thing. Both of them started as this, okay? The difference is that the circled intermediate went directly to this, whereas this green one came about after resonance. So what does that tell you about speed? Which one of these is achieved faster? The one that requires no resonance, because it forms the intermediate and it becomes a product, right? Intermediate and product. That must mean it happens faster. What about this one on the right? It formed the intermediate, then it resonated, then it became the product. So that means it happened slower. Okay? So we have the terms kinetic and thermodynamic. What do you think kinetic means? Kinetic sounds like fast, sounds like speed. Thermodynamic just sounds like high temperature and stability. So you can think of it like that. Okay? This is the kinetic product. You start using different colors, man. That is the kinetic product, and this is the thermodynamic product. Now, what you need to know about kinetic and thermodynamic, okay? Kinetic products are less stable, okay? Emphasis on product. Less stable product, achieved faster, and under low temperature conditions. Thermodynamic, on the other hand, is going to be the opposite, okay? More stable product. Slower. And I'll just add this in, right? Due to resonance. Right? Resonance is an extra step, takes some energy, takes some time. And this occurs under high temperature conditions. So put like negative 40, for example, and like 100 degrees, for example. Okay, now what do I mean by more stable product? People, when they hear more stable, they think about the intermediate, which is good, right? Usually we think about that, but that is not the product. That is an intermediate. You are very correct that the kinetic one has the more stable intermediate because it came from a secondary allylic carbocation, whereas thermodynamic came from primary allylic. So in terms of intermediate, sure, the kinetic one is better. But we're talking about product. What is this product? It's an alkene, okay? They're both alkenes. The alkene from the kinetic side is monosubstituted, okay? The double bond only has one substituent. On the thermodynamic side, it's disubstituted. It has two substituents. And as you hopefully remember, the more substituents you have on your double bond, the more stable it is. Right? Cis and trans don't even matter yet. It's just number of substituents. That is why thermodynamic is the more stable one. It's achieved slower because of what I just said, right? It takes like an extra step. And because it's slower and it ends up being more stable, you need like a higher temperature. And the kinetic is just the opposite of that. So I'll go ahead and just tell you the shortcut right now. Kinetic is from the best intermediate. And thermodynamic, you start with the best intermediate, then resonate. Okay? So for kinetic, it's just like one step. For thermodynamic, it's like one extra step. I'll go ahead and give you some examples or other things to do. Let's see. Okay. Let's do this right here. And we're going to we'll just do both of them, right? We'll do both products. So when we react with HBr, okay, just find the best possible position. This will be primary, tertiary, secondary, secondary. What is the best? The tertiary one. So I'm going to form my carbocation over there, right? Don't think too much about it. That's all you're going to do. So you form your carbocation right here. And If we want the kinetic product, let's put a K for kinetic, then you're done. Add your bromine or whatever, what is it, bromine? Add your bromine there, and you're done. If we want the thermodynamic product, resonate it once. So what are we going to do? We're going to put this double bond there. God dang. There we go. And then we're going to add our bromine. That's it. Right? So I gave you a little shortcut, but we can also just confirm it. This double bond is di-substituted, okay? Whereas this one is tri-substituted. So as you can see, that method works. Let's do another one that some people were getting wrong. See if I can remember the question. I believe it was this. Okay, so I'm gonna go ahead and draw your product, and you can tell me, is it kinetic or thermo? So take a look at it real quick. Okay, the answer is it's neither. At least when we're talking about major products, this is neither. I'll tell you why after I actually solve this. So this product is actually attainable and it is very stable. You have a conjugated set of double bonds, but it is not a major product at all. So let's go ahead and answer this how we would answer it, okay? You have your H plus. What is the best possible position? Secondary, secondary, tertiary, secondary, secondary. The tertiary, right? Don't think too much again. Just take the tertiary spot. Make your carbocation there. Because you have to remember that the more stable the intermediate is, the faster it will occur, and the more likely it is that you will form that, right? Sure, secondary is somewhat stable, and I might be able to achieve that, but since the tertiary position is the most favorable, that's the one that's going to be achieved most of the time, which is why when it comes to major products, you look at the most stable intermediate. So we're going to do that. Okay, we have our carbocation right here. For kinetic product, where we have, let's do negative 40 degrees, you're done. Attach your bromine or whatever the halogen is, and you're solid. Now, if we do 200 degrees Celsius, thermodynamic, we're going to resonate. Now, this molecule is symmetrical, so it doesn't matter which side I resonate, but we're going to resonate one of these just one time. So bring this down here, and we get that, which ultimately ends up as this. Now take a look at this. This molecule has two double bonds in conjugation, okay? And these double bonds are both di-substituted. Well, this is di-substituted and this one is tri-substituted. What about this one? We have two double bonds in conjugation. This one is di-substituted and this one is tetra-substituted. So you might be thinking, why is this not like the thermodynamic product? It looks actually even better than this one. And I thought you said that thermodynamic is the more stable product. It goes back to the intermediates, okay? If you wanted to achieve this product, your intermediate would involve forming a carbocation right here, where you form a secondary carbocation. And you have this. But this is not going to occur because this is a possibility, okay? Since the tertiary position is able to be formed, you're not going to do this. It looks like a good product, but logically and like chemically and literally, like it's just not going to happen in major amounts. Very, very, very minor. So what am I trying to say here? Just do it step by step, okay? Form your intermediate and then move on, right? When it comes to most stable product, use that at the end to just confirm your answer, but don't try to find the most stable product from this alone. Form your logically most stable intermediate. Then if it's kinetic, leave it as is, add your bromine or iodine. If it's thermodynamic, resonate once, and then you're done. Did I make myself clear? Hopefully I did. Cool. Question that might be asked. What is 74 degrees? Is this kinetic or thermodynamic? What about 15 degrees? What about 34 degrees? It doesn't matter, bro. Like, don't worry about this. Like, what do you call this, bro? I can't even speak. Don't worry about this unnecessary stuff. They're gonna make it super obvious. Okay, they might literally tell you kinetic product and thermodynamic product, or they'll just make it extreme. Okay, -40, you cannot mistake this with thermodynamic. 200 or even 100, you cannot mistake that with kinetic. So they won't give you something in between where it's ambiguous. They'll make it super obvious. Okay. Cool. Let's talk about one more thing. The thing I want to talk about is like a ranking thing, which is a whole topic I have set up at the end, but we're going to go ahead and bring it up anyways. It's UV Vis, right? So UV Vis is just like a type of like analytical method. It's kind of like IR and NMR. But what happens, right? When it comes to UV Vis, they ask you to rank. They ask you to rank by lambda max or wavelength, right? And they'll be like, which molecule has the shortest wavelength or which has the longest and whatever. Okay, and they'll give you some molecules. I'm stealing this right off of PLTO because I have them all memorized at this point. All right, give me a moment while I draw these molecules. So hold up. Okay, we'll do, let me tweak this a little bit. Okay, I think this is good. Okay, so they'll give you these molecules and they'll be like, rank 1 equals longest and rank 3 equals shortest. So to keep it simple, more conjugation equals higher wavelength. Okay, conjugation means alternating double and single bonds. So double, single, double, single, double. This has less conjugation. Thing I just drew at the bottom, right? Over here you have 3 double bonds in conjugation. At the bottom you only have 2 in conjugation. So the more conjugation, the higher the wavelength. The less conjugation or the lack of conjugation, the lower the wavelength. Now I have to be a nerd and kind of explain something real quick or make a connection. If you don't care, please skip. So there is an equation that you probably learned from, I don't know, Gen Chem or something. It's C equals F times wavelength. Now, when we go back to the IR world, when we had a double bond C, it was 1660 as our value, inverse centimeters or wave numbers. But then when we had a benzene, the C double bond C was now 1600. Okay, so what happened? The value decreased. What is the unit of this value? It's frequency. Okay, when we go back to this equation, we have frequency and we have wavelength. When they're on the same side of the equation, they're inversely related or inversely proportional. So if frequency is decreasing when it comes to conjugation, as we have in this double bond, that means that the opposite will happen to the wavelength, or an increase will occur. Okay? So that's what I want you to know. Another connection we can make is this: E equals hc over lambda. So when you have conjugation, the energy of your molecular orbitals will decrease. So you can literally just bring this to the other side, right? We'll just do that. E times wavelength equals hc. So if our energy is decreasing, that means our wavelength will increase. Okay, so a couple connections I wanted to make as a nerd. So essentially, you were trying to find the one that has the most conjugation. Let's go ahead and do that with this question right here. So these two are not in conjugation because I have two single bonds between them. What about over here? Double bond, single bond, and I'm stuck. Two single bonds, right? So this first molecule seems to have no conjugation at all. So I'll just put like 0 double bonds in conjugation. Over here, these two are away from each other, but I have double, single, double. So I'll put 2 here, 2 double bonds in conjugation. What about over here? Isolated again, but double, single, double, single, double. So this has 3 double bonds in conjugation. So the one with 3 is the best. So this is gonna be rank 1. This will be rank 2, and this will be rank 3. Okay. That's all. Okay, let's talk about one more thing maybe. Let's do this. Let's talk about these. What if we're ranking these? So as you can see, all 3 of these molecules have the same number of conjugation, right? They both have 2 double bonds in conjugation. So if the number of double bonds in conjugation is the same, now you have to look at another factor, which is essentially things that make it stable, okay? So, okay, to keep it simple, alkene stability, okay? So this alkene right here is mono substituted. So I'll put an M right here. This alkene is di-substituted. What about this one? Di-substituted and di-substituted, di and di, right? So the more substituents you have, the better. The first molecule has D and M, whereas the rest of them have all D. So this is going to be the least stable. So put 3 over here. Now between these two, they're both di-di, okay? So what is a distinguishing factor? It's going to be cis and trans. Well, these are both trans because they're going in opposite directions. But if I compare these two, the top one is trans and the bottom one is cis. So this molecule is trans, whereas this one is trans cis. So the more trans, the better. That's just how it is, right? Less sterics and stuff like that. So this will be rank 1 and this will be rank 2. Okay. So step 1 is look at most conjugation. Step 2, the tiebreaker will be alkene stability. So number of substituents is the first thing you look at, and the second thing you look at is cis and trans, right? Don't look at cis and trans if your number of substituents is not the same, okay? If this is the same, then you move on to cis and trans and all that. All right, as far as I'm aware, we're done with conjugated systems. Let's move on to Diels-Alder, which is a big portion of this exam. For a Diels-Alder reaction to occur, you're going to have what's called a diene and a dienophile. The diene is a conjugated dialkene. As you can see, they're conjugated double bonds. Okay, this is not considered a diene. Yes, it is, but not for Diels-Alder. This is not going to be a correct thing. So make sure it's a conjugated diene. And they're going to have your dienophile. Dienophiles are either alkenes or alkynes. So we'll talk about alkynes later, but just keep in mind that's what a dienophile is. And this is the most simple version of this reaction. By the way, Diels and Alder won a Nobel Peace Prize or something for this. And it's pretty cool. Diels was like Alder's chemistry student or something. Or I might have flipped it, but then they like made this reaction. It's low-key tough. So anyways, what happens is we're going to number these carbons 1, 2, 3, 4, A, and B. B is going to take this pi bond and form a bond to carbon 1. Now, carbon 1 will have too many bonds because it already has 2 hydrogens and it has a double bond, and we just added a 5th bond. So we're going to shift this double bond over here. Now, carbon 3 runs into the same issue where it gained an extra bond, so we're going to shift this over here. And it's good because carbon A already lost its bond since carbon B used it to bond to carbon 1. So it works out. And notice how we had 3 pi bonds. Okay, 3 pi bonds, but 2 of the pi bonds were used to form sigma bonds, which means that our product should only have 1 pi bond. So our product is going to be a cyclohexene. Somebody said that the product is a benzene. I started dying because like you're cooked. But you're going to have a cyclohexene. Now this is the most simple version of this reaction. By the way, you have to do it under heat. Now this specific version of the reaction actually takes high levels of heat. The reason for this is that the HOMO of the diene and the LUMO of the dienophile are actually not that close. So we have something called a HOMO, right? I'm just going to make this up here. HOMO, and then we have LUMO. So HOMO means highest occupied molecular orbital. And so out of all of these, the HOMO is this one. And the lowest unoccupied molecular orbital is this one because it's the lowest. So if your HOMO and LUMO are pretty close together in energy, then this sort of pericyclic reaction can occur fairly easily. But if they're far apart, then it's either just not going to react or it takes extreme conditions to occur. So right now, our diene and dienophile are not, they're not primed to do a really easy Diels-Alder reaction because of the distance in energy of the LUMO and the HOMO. So normally what we do is we add electron donating groups to our diene, and we add electron withdrawing groups to our dienophile. When you do this, you lower the energy between the HOMO and the LUMO, and excitation and all that stuff can occur, and you get your reaction. So let's go ahead and draw one example. We're going to use OCH3, and we'll react with this. So over here, it actually matters, right? We can't just necessarily say that this carbon bonds over here and this carbon bonds over here. Because what if it's flipped? What if you're flipping the carbon that you're bonding to? What if it's actually like this and like that? This is where finding the activated carbon comes into play. So we're going to number normally, right? 1, 2, 3, 4. And we'll call this carbon A and carbon B. I'm going to show you a little like trick that I like to do. There's multiple ways that you might have seen this, but I'm going to show you the one I go with and I think is the easiest to understand. This OCH3 is electron donating. Whatever I show you applies to any donating groups, even if there's no resonance available, right? I'm about to show you a trick with resonance, but listen, this is not actually what's occurring. There's no actual resonance that occurs to do this all the time, but this is a way of thinking about it that will get you the correct answer every time. So you're going to take this lone pair, bring this down, and just resonate all the way through. And you ultimately end up with a negative charge on carbon 4. So carbon 4 is the activated carbon of our diene in this case. Now NO2 is electron withdrawing. So it's going to withdraw electron density. And when that happens, you get a plus over here. So carbon A is the activated carbon of the dienophile. Now you can match up the carbons based on opposite charges. So we can say that 4 bonds to A. And we have 1 and B left, right? So 1 and B will bond to each other. So remember, we're always going to form a cyclohexene. This is like the base, okay? Any question you get, just form a cyclohexene minimum. Don't draw anything else. Draw this and you'll get partial, hopefully. So our cyclohexene, right? I'm going to cut it real quick. The left side comes from the diene and the right side comes from the dienophile. Because remember, the double bond came from the shifting of the double bonds, right? So this is that diene double bond. So now we can number, right? 1, 2, 3, 4. And we said 4 bonded to A and 5 and 1 bonded to B. Now we can add our substituents. So carbon 1 has an OCH3. So I'm going to add an OCH3. And carbon B had an NO2. So now I'm good. I'm purposely ignoring stereochemistry because I'm just showing you how to figure out activated carbons. So this is our answer without any stereochemistry. Let's take a look at another example. What is the activated carbon of this one? My carbon, this is an electron donating group. It does not have lone pairs, but like I told you, just treat all the donating groups the same. Pretend that there's resonance and go all the way through, right? Resonate and like this, and you'll always get the furthest away as being the activated carbon, okay? Just want to mention that, so you get the same answer. Let's make a different molecule, like where the substituents on a different position. Let's do this. And we'll do CN. Okay, let's figure out the activated carbon. Do some resonance, okay? We'll go over here. Now, what do we do next? There's nothing to do over here because we're not next to any double bond over here. We are next to this double bond. So we're going to shift it like this. And our activated carbon ends up being that one right there, right? So 1, 2, 3, 4. Number 1 is our activated carbon. Over here, the dienophile is the same as before. Just withdraw, and you'll get a plus right here. So carbon A, carbon B. It seems that carbon 1 is bonded to carbon A, and carbon 4 is bonded to carbon B. So when we draw our cyclohexene, we're going to make sure that that matches up. So we'll draw our cyclohexene. We'll say carbon 1, carbon 2, carbon 3, carbon 4. Now let's match it up. Carbon 1 is bonded to carbon A. So I'll put A over here. And carbon 4 bonds to carbon B. So this will be over here. Now match up your substituents. Carbon 2 has the ethoxy group. So we're going to add O, CH2, CH3. And carbon B has a CN. So we're going to get CN. So this is our answer without stereochemistry. Now, I'll actually just go ahead and tell you the little shortcut. This top one is a 1,2 product, and this bottom one is a 1,4 product. When you have two substituents total, one coming from the diene and one from the dienophile, you're either going to get a 1,2 or a 1,4 product. And your 1,2 product will specifically look like this, okay? Let me show you what I'm talking about. This is technically a 1,2 product, but it doesn't make any logical sense. Why? Look. The left side comes from the diene, and the right side comes from the dienophile. So it doesn't make sense that both substituents are on the diene carbons. Okay? So it has to look like this. And this bottom one is 1,4, and it has to look like this, where one substituent is from the diene, and the other one is from the dienophile. Now, how do you know if it's going to be 1,2 or 1,4? If your substituent is on the outer carbon, right? So over here or over here, you're going to get the 1,2 product for reasons we just explained, right? With the whole activated carbon. If your substituent is on the internal carbon, so carbon 2 or 3, then you're going to get the 1,4 product. So if I were to give you this plus that, we can figure it out easily. Okay, we're going to draw our cyclohexene, and this is internal, so that means 1,4. So I'm going to go ahead and draw my thing right here, and this should be para to my thing, right? So CF3. That's my answer once again without any stereochemistry. So now let's include stereochemistry, okay? So this is what's happening, right? We're going to go ahead and draw a little dashed binding pocket. This will be like our little boundary. And I'm going to add some more substituents. Okay. Now, first of all, if you're wondering, is this a 1,4 or 1,2 product? Sorry, let me add this as well. Okay, if you're wondering, is this a 1,2 or a 1,4 product? You have a lot of electron donating groups here. So if you want to do 1,2 and 1,4, look at the best of them, okay? The oxygen one will be the best. If you had a nitrogen, I believe that would be the best. This is the best. So when you're doing 1,2, 1,4, base it off of this. Since the OCH3 is on the outer carbon, you're going to have a product that's 1, 2, meaning that you'll have all these other substituents, but the OCH3 will be 1, 2 to the NO2. And you can match up the other substituents. But don't worry about that right now. Let me just go ahead and draw my thing without any stereochemistry. And then we're going to explain how stereochemistry works. So you notice how my OCH3 and NO2 are 1, 2 to each other? I could have put the NO2 down here and made it 1, 2 to one of these, but I didn't do that because it's not the best EDG. Okay, so this little binding pocket that I drew, for the diene, okay, forget the dienophile right now. For the diene, if I am internal, like these green ones, if I'm going inside the binding pocket, that is going to be on a wedge. And if it is outside, like the OCH3 or this ethyl, outside the binding pocket is going to be dash. This rule, I don't know who's watching this video. If you're like not from my school, then maybe it's different what your professors say. But for us, this is the rule. This is the rule because there are assumptions that are being made that cause this to always be the answer. So based off this alone, I know that my methyl here will be on a wedge. And I know that my methyl down here will also be on a wedge. We'll fill that in. Now my methoxy group, right, the methoxy and the ethyl, these are both outside of this dashed binding pocket. Those are going to be on a dash. So I'm going to go ahead and put them on a dash. That is all you need to know for stereochemistry for the diene. You're probably wondering, what about this methyl right here? This methyl is on an sp2 carbon. So by definition, it can't have stereochemistry because it's planar, it's flat, you know, sp2. So this is our answer if we are just considering the stereochemistry on the diene. Now, what about the dienophile? The dienophile does not have to use this little binding pocket rule that we talked about, because take a look at this. This NO2, the whole molecule can just flip itself to the other side if it wanted to. And like at that point, we can't really say, oh, it's inside or it's outside the binding pocket. That's not going to help us because it can just flip to the other side, right? And I mean that the whole molecule is flipping. Like this is like rotating itself. I'm not saying that the NO2 literally moves to the other side. I'm saying the whole molecule is moving. So that's not going to help us. When it comes to the dienophile, we're going to use what's called the endo and the exo rule. And this strictly applies to the electron withdrawing groups that are on your dienophile. So the endo rule is going to be for things with a pi system. So examples of this are carbonyls, CN, which is C triple bond N, and NO2, which is going to look like this. Look, you have a pi bond right there. If you have any of these, you're going to be following the endo rule, which means that you're going to be on a dash or down. Now the exo rule is low-key uncommon, but it's things without a pi system. So examples of this would be CX3. This is the only example that we're told. So X can be your halogens. Now what does this look like? It just looks like this, right? There's all single bonds. There's no pi system. So exo rule means that you're going to be on a wedge or you're going upwards. Okay? So essentially, let's say that this is not the correct positioning and the correct positioning was this way. Then the NO2 will just flip itself. It will flip the whole molecule so that the NO2 is facing inside. That's why we can't go by the position they give us. You have to go by the endo and exo rule. So knowing that NO2 is a pi system, it's going to have its substituent on a dash. So this is our like full final answer. Okay. What about this? So look, on my diena file, I see I have some electron donating groups like methyl and ethyl. Listen, these do not follow a particular rule like endo and exo. The rule is followed by the electron withdrawing group. The electron donating groups will just follow depending on where they're forced to be. I'll tell you what that means. Let me draw this product real quick. So I see that we have, I'll draw my little binding pocket. One of our methyls is going to be inside and one will be outside. So it doesn't really matter which one I choose to be which, but I'll just go ahead and put this one on a wedge and this one on a dash. Okay, and this one refers to that one and this one refers to that one. Now my diena file side, I have an NO2 and I have ethyl and methyl. So the NO2 wants to be on a dash because it's following the endo rule. So we're going to put this on a dash. Now take a look. On this diene, my NO2 and my diena file, my NO2 and my ethyl are cis to each other. So that means that on my final product, they should stay cis. Whereas my NO2 and my methyl are trans to each other. So on my final product, they should be trans to each other. So since my ethyl is cis, it's going to follow the NO2, making it on a dash. Since my methyl is trans, it's going to be opposite, which means on a wedge. So that's what I mean. The electron donating groups don't follow a rule. They just go based on what the electron withdrawing group is trying to do. And then we'll just do one final example for now. So we should be able to do this really quick. My electron donating group on the diene is on an external carbon. So we're going to have a 1,2 product. So I'll just go ahead and put I'll do like this and this, right? I see that my NH2 is going downwards. It's inside this binding pocket. So it's going to be on a wedge. My CF3 is going to be on this carbon and it's looking like this where there's no pi system. So it's going to be on a wedge following the exo rule. So CF3, exo. And my methyl is going to be on the next carbon and it's cis to the CF3, so it's also going to be on a wedge. So that's how you do stereochemistry. All right. What if you have a diene that looks like this? What is your answer going to be? Let's add carbonyl here. So we're going to draw our cyclohexene, as always. And I'm going to number this time, right? 1, 2, 3, cooked. 1, 2, 3, 4, and then A and B. So my cyclohexene that I draw will always be 1, 2, 3, 4, A and B, right? So we got 1, 2, 3, 4. Over here, it doesn't matter what bonds to what because the diene is symmetrical. So we'll just say 1, 2, 3, 4, and then A and B. And then we'll fill this in, right? B is going to have a dashed carbonyl. And we're missing two things right here. We're missing these. We're missing 5 and 6. So 5 and 6 are going to look like this. 5, 6, boom. Where 5 is bonded to 4, which is 5 is bonded to 6, and 6 is bonded to 1. So it's like a ring within a ring. Then if you want to show stereochemistry, which you should, you're going to put these on a wedge. Right, so this is carbon 5, carbon 6. You're going to put it on a wedge. Let me fix this a little bit. Maybe you can draw it like this. Okay? And we put it on a wedge because, look at this. 5 and 6 are within the binding pocket. Pretty much anytime you have a double ring, that double ring will be on a wedge because I don't know how it can be on a dash. Doesn't make any sense. So it's going to look like this. Now, there is another way to depict this molecule, and it is using our chair structures. So if you don't like chair structures, you don't have to draw them, right? Just stick with this right here. But everyone should still know how to interpret chair structures, because they can give you a question like this and they're like, how do you make this? And you have to know what you're looking at. So I'm going to go ahead and show you anyways. Okay, when you get a chair, this base structure right here is your cyclohexene. So a good practice, as always, is to number, right? 1, 2, 3, 4, and then A and B. So as you can see, the left side is from the diene and the right side is from the dienophile. Now, carbon B has this group right here, which is the carbonyl. On a chair, if you remember from OChem 1, you do not show wedges and dashes. Instead, you show up and down, right? So a dash is down and a wedge is up. So we determined that our carbonyl should be on a dash, so it's going to be going down. Don't worry about axial and equatorial. They're not that picky about it. Just make sure it's obvious that it's going down. So don't do this. That's clearly not down. So make it look like this for carbon B. Now carbon 1 and 4, what is their bicyclic thing going to look like? It will look like this, where this is carbon 5 and carbon 6. But notice how 5 and 6 are going upwards. Or maybe they'll draw it like that, right? It doesn't matter. But that's what it's going to look like. So it's like a double ring. It looks pretty interesting. So like when we get to this, we kind of like know what we're looking at, right? Like if you look at this, we can tell that this circled ring must have come from something like that, right? That doesn't make sense. Don't worry, we'll get there. But the rule of thumb is to always look at this first. Thing I'm highlighting in blue. This is your cyclohexene, your base. All right. Now a question that might be asked: what happens if I have a diene with an electron donating group or withdrawing group, and I have a dienophile with an electron withdrawing group? Or what if I have a diene with an electron donating group and I have a dienophile with an electron donating group? They're never going to give you these because they just don't work. What did I mention earlier? The whole thing that's going on is one of the molecules is electron deficient and one is electron rich, because you're trying to bring the HOMO and the LUMO closer together. So if they're both the same, if they're both electron rich or they're both electron deficient, the HOMO and LUMO will be further away from each other. It doesn't make any sense. So they're never going to give you this. It's not going to work. It's like literally impossible. So don't worry about that. However, as I showed you already, like they could mix it up, right? Like usually you don't see electron withdrawing group on a diene, but you do sometimes see electron donating groups on the dienophile. So like, CF3, and then those put like some carbons and stuff like that. This is fine. Just, we already showed how to do this. Like just ignore the donating groups when you're figuring out what carbons to bond to what, and then just treat them as they are, right? If they're cis, then they'll be cis to the CF3. If they're trans, they'll be trans and stuff like that. So I hope that answered your question. What is the product of this? We should be professionals now. All right. What if we have an alkyne? If we have an alkyne. So it's the same thing as the alkene, except like when you're forming your bond and all this stuff, you're still going to have one of the pi bonds remaining. So normally we get a cyclohexene, but this time we're going to get a cyclohexadiene because we still have one pi bond remaining. Okay. And the good thing about this is that you don't have to worry about the stereochemistry on the dienophile side. So if I do, I don't even know. If I do this, I'm going to get cyclohexadiene. The left side still follow the same rule, right? If it's within the binding pocket, then it's going to be on a wedge. So you got wedge and wedge. But over here, my two substituents are going to be on sp2 carbons, so I don't have to worry about that. So that'll be like my answer. Let me drop a ranking question real quick. So you might get a question that's ranked by lowest LUMO, and they'll give you some, the heck? I'm kind of scared. Let me go in airplane mode. Okay, they're gonna give you some diene, so we'll go like, or why do I keep mixing them up? Dienophiles. We'll just do this for now. Actually, we'll do that. Okay, ranked by lowest LUMO. 1 is lowest, and what do I have? 4. 4 is highest. So remember, the more electron deficient your dienophile is, the lower the LUMO will be, right? Take a look at this. We're trying to bring the LUMO, you're trying to bring the LUMO down and the HOMO up. The LUMO is coming from the dienophile, and the HOMO is coming from the diene. So if our LUMO has, if our dienophile has a lot of electron withdrawing groups, or has just like a good quality of electron withdrawing groups, then the LUMO will be brought down. If it sucks, if it has a lot of electron donating groups or stuff like that, then it'll be going the opposite direction. HOMO is going to be the opposite in that you want it to increase in energy, and that would happen with electron donating groups. If you have withdrawing, it will decrease it. So when we look at this, rank by the lowest LUMO, you want to look at the one that has the most electron withdrawing groups or the best electron withdrawing groups. So over here, I see that this is the only one that has an electron withdrawing group with the NO2. The other ones, I have a methyl here, and I have an OCH3 here, and then over here I have nothing. So we have electron withdrawing group, we have electron donating group, and nothing. So my best would be the electron withdrawing group one, because it really brings it down. My second would be nothing, because having nothing is better than having something that's bad, right? Electron donating group is bad for the LUMO stuff, okay? Now between the two electron donating groups, which one has a stronger effect? This is stronger. So this will increase the LUMO by a lot, making this the worst one, and this will be the like rank 3. They could ask you rank by highest HOMO energy, or I don't know how they word it, but something like this, and they'll give you some dienes. Okay. So remember, the HOMO being high is good because we're trying to bridge the gap between HOMO and LUMO. And so we want the one that has the most or the highest quality electron donating groups. And withdrawing groups are going to be bad, right? So over here, I have 2 electron donating groups, and they're really good. They're OCH3s. Over here, I have 1 withdrawing group and 1 electron donating group. Over here, I have 1 electron donating group. Oh my God. I know what I'm saying. I just keep like saying it wrong out loud. Withdrawing, and 1 electron donating group. Okay, so 2 electron withdrawing groups is the best. What else do we got? I see that we have something with just electron donating group. So this will be rank 2 because the rest of them have withdrawing groups. Between the 3 that we have left, this would be rank 3 just because it has at least a donating group. Then we're left with solely electron withdrawing groups. So NO2 is like the strongest of all the withdrawing groups. So this would be the worst, rank 5. And this would be rank 4. Maybe the hardest part is knowing if it's supposed to be higher or lower, but just draw out the HOMO and LUMO and it will make more sense. All right. So I want to. Okay, I'm going to mention this, so I'll mention it again, but remember that Diels-Alder is driven by heat, okay? And this is called a 4+2 reaction. It's called 4+2 because one molecule will use 4 pi electrons. So like this is 4 pi electrons. The other one will use 2 pi electrons. So we'll use this. And these 4 and 2 are going to work together to form like a cyclic structure. Do not do this reaction if you're given HV or like UV light. So a little foreshadowing. We're going to do some like synthesis real quick, and then we'll talk about this. Remember, Diels-Alder is heat. So let's figure out how do we make these molecules from Diels-Alder. And as you can see, they'll have heat conditions, so it's regular 4+2 stuff. So the way I would do it is, you can figure out, right? Oh, I messed this up. I was supposed to put it here. Okay. So the way you would do this is, in this case, like we have a cyclohexadiene. So we can't like necessarily say that this is the diene. It could be the other way around. Okay. But how do we know? Just take a look at the substituents. So on this right side, I see that we have electron withdrawing groups. Whereas on the other side, we have donating groups. So now I can actually determine what part came from my diene and what part came from my dienophile. So this that I'm numbering right now, 1, 2, 3, 4, that came from my diene. And then A and B came from my dienophile. So the first step is to draw in your base diene, number 1, 2, 3, and 4. And we can like low-key just like split this like this. Split it like that. I don't want to draw it too dark, but let's just split it like this. Okay. So the left side is going to be our diene, and the right side will be our dienophile. Now we can just complete this. Okay. So carbon 2 and carbon 3 are bonded to this little pentagon ring structure. So we can complete that ring. Carbon 1 and carbon 4 both have a methyl, but they're opposite to each other. So carbon 1 is on a wedge, which means that it's going to be going downwards like this, or within the binding pocket. Carbon 4 is on a dash, so it'll be outside the binding pocket. So like this. So that is going to be our diene. Now we can do our dienophile. Notice how our dienophile still had the double bond there, which means that it must have come from an alkyne. So we can draw our alkyne. And we don't have to worry about like, you know, cis and trans or whatever, because this is sp, it's linear. So now we can just draw in our esters as they are. So you got our ester like that, and ester like that. And unless I forgot something, this will be our answer. The next one, remember, locate like the base structures. We have this. We can split this because we know that the left side came from the diene because the double bond is here. So we can number 1, 2, 3, 4, A and B. Start with your base diene. So that. And then we have this oxygen that's bonded to both carbon 1 and carbon 4. So we're going to show that in our diene. We're going to draw an oxygen that's bonded to carbon 1 and carbon 4, just like that. So that is going to be our diene. And then our dienophile, there is no double bond between carbon A and B, so our dienophile will have been a double bond because it gets removed. And then we can just draw, right? This is symmetrical, so it doesn't really matter. What is this? 1, 2, 3. So it's going to be, oh my God, like that. And then we can add in our carbonyls. And carbon A, carbon B. All right. Now this one is interesting because you know the double bond's on the right side. We only have one double bond. So the numbering is going to be flipped. We're going to call this carbon 1, 2, 3, and 4. And the other side will be A and B. And it makes sense, right? Because we see an electron withdrawing group on this side, which is going to be from a diene-a-phile. And we have NH2, which is going to be usually from the diene. So, yeah. So I'm going to draw my diene like this. We'll number this carbon 1, 2, 3, and 4. Carbon 1 has a dashed propyl group. So it's going to be outside the binding pocket. So I'm going to draw 1, 2, 3. Okay. Carbon 3 has an NH2, so we'll draw this. Carbon 4 is bonded to something right here. It's like carbon 5 and carbon 6. So this would be like our little cyclohexane type structure. So we can go ahead and fill this in like that. And this will be what? Carbon 5, carbon 6. It's going to look like that. Okay, now we can go ahead and draw our diene-a-phile. So diene-a-phile will be a double bond. And we'll just call this carbon B and carbon A. So carbon B has a CF3 and a methyl. So we'll do CF3 here and then methyl there. Now look, my methyl on carbon A is cis to the CF3. So I need to make sure that's the same on the alkene. So I'll make my methyl over here cis to the CF3, and then the other thing would be trans. So this is our answer. And I do this backwards, right? Normally we have our diene on the left and diene-a-phile on the right. I do it backwards, but still correct. Right, this is our little binding pocket, and yeah. Okay, so now we'll briefly talk about some other pericyclic reactions. So remember that Diels-Alder is a 4+2 reaction, and it has to occur under conditions of heat. But if I gave you this diene and diene-a-phile and I reacted it under light, sometimes I'll write it as UV light, then we're actually going to do something called a 2+2 reaction, which is considered forbidden. And we talked about what 4+2 means. So 2+2 means you're going to take 2 from one side and 2 from the other, right? 2 pi electrons. So we'll just count this as 1 and 2. And this will be A, A and B. So 1, 2, A, and B are the ones participating in this, right? This thing is just a substituent now. It's not part of this whole system. So carbon B will bond to carbon 1, and carbon 2 will bond to carbon A. And it doesn't matter which one bonds to which, because it's like symmetrical. But look at this. We have 2 pi bonds, and we are making 2 bonds. So both of those pi bonds will be used to make those new ring sigma bonds, which means that our ring is going to look like a square, but it's not going to have any double bonds present because the double bonds are gone. So this will be 1, 2, A, B. And now we can just complete it, right? Carbon 2 is bonded to this ethanol group. So we'll get this. And that is our product. Okay? Be very, very careful because I've seen an old exam where question 1, heat, question 2, heat, question 3, heat, and you're in the flow state of just doing Diels-Alder with heat. And out of nowhere, they'll throw this at you. And you don't even notice it because it's such a small set of 2 letters. So be mindful of this and know that it does something different. Another question I've seen, they'll give you this and they'll be like, what is the answer? So this is interesting because there's only one reactant and then there's light. There's no other molecule. Whenever you see something like this, the molecule is reacting with another molecule of itself because this thing is there in excess. So another way you can look at it is draw the same thing twice. Okay, and this is a 2+2 reaction. So take 2 pi electrons from one and 2 from the other. So we'll number this as 1, 2, A and B. Form a bond, form a bond. And that is actually going to be our answer if you just complete this and remove the double bond. So I'll go ahead and draw it out again. So we have carbon 1, carbon 2. Carbon 1 is bonded to carbon B. And carbon 2 is bonded to carbon A. So these 2 pi bonds are gone, but the outer ones are still there, so we can keep them in. And this is our this is our final answer. By the way, I think for this specific example, if you were to do heat, it still wouldn't work just because of the structure of it. Like you try to, I don't really know how that would work because you can't form like a bicyclic thing when you have 4. I don't know if that makes sense, but it just wouldn't work. So I'll make a connection to biology. They say sunlight is good for you, but too much is bad. It's good actually because it drives some of these 2+2 reactions that build like proteins and stuff. I don't know what it is, but they build something that we need. However, if you have too much, this is what you can potentially have happen. So I'm going to go ahead and draw thymine. Hopefully, oh my God, I'm cooked. I'm so cooked, I can't draw. Thymine is one of our nucleotide bases. All right, it looks like this. And I'm gonna go ahead and draw another one. Hopefully you can sort of anticipate what I'm about to do here, but maybe you don't know. It's all good. I'm about to show you. So I do the same thing, but just flipped. Okay, double bond, double bond. If you have a lot of UV radiation coming from the sun and you're not blocking it with like sunscreen or whatever, this is what can happen. You're doing a 2+2 reaction. You're going to bring these together. I'll put these metals out of the way. And you're forming this right here. This is called a thymine dimer. And these are, they're bad, right? They get in the way and they interfere with your DNA and basically like causes cancer and stuff. So that's why they tell you like wear UV protectant sunscreen, because you don't want to have this happen to you. It's kind of interesting to think about like once you learn it. So yeah. Oh my God, I'm so dumb. Here, that's the answer. All right. Okay, so that's 2+2. I think that's the only like other one you have to worry about, but like I'm gonna go ahead and drop 6+4 and 6+6. So on an exam from 3 years ago, they gave a molecule that looked like this. It was a triene, and they just gave 2 of them. And it just like specified, it was like when they react under thermal conditions, which means heat, it makes the 6+4 product. And if it reacts under HV, it makes a 6+6. I could be having it backwards, but what I'm trying to tell you is that they explicitly stated what type of reaction can occur. Because to be honest, 4+2 and 2+2 are not the only things that can happen. Like 2+2 is not the only thing that happens with HV. You can have other wacky things like 6+2 and 6+4 and all that stuff. So I highly doubt they're going to make it ambiguous to you. They'll just tell you if anything. So if they specifically tell you to do a 6+4 or 6+6 product, you know what to do now, right? For 6+6, we'll start with that. We're using 6 pi electrons from both. So we're going to consider the entire molecule on both sides because that's 6 pi electrons. So we'll number this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Now, do what you would expect to do, right? Form a bond between 12 and 1. Shift this bond over there. Shift it here. Shift this over here to form a bond with 7. Move this down. Right? It's just Diels-Alder, but on steroids. Now, when you do this, you might think that you form a 12-membered ring because you're doing 6+6, right? 4+2 formed a 6-membered ring. So 6+6, you might think forms a 12-membered ring. But to be honest, like you don't really form rings this big, or at least you don't form a ring that looks like this. Okay, let me show you what you actually end up with. I'm gonna draw one side the same. Actually, I'll draw them both the same. You're gonna keep them the same and then just form like a little bond between them. So it's kind of gonna look like a square like this in the middle, but it's not like a full square. It doesn't have the vertical lines. It looks like this. Okay, and we can number it, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And just match up where you move the bonds. So I see you shifted a bond between carbon 2 and carbon 3. So we'll have a bond right here. Carbon 4 and 5 have a bond. 6 formed a bond to 7, but 8 and 9 have a bond. And 10 and 11 have a double bond. So this would be my answer right here. So it's like two 6-membered rings that are like fused, but it's not like fully connected. Like it's like a continuous ring, but it's like a different shape, if that makes sense. So it's gonna look like this. Now for 6 plus 4, I'm gonna draw the trienes again. In 6 plus 4, you'll take all 6 from one side, but you're only gonna take 4 from the other side. So we'll just take 6 from the left side, right? So 1, 2, 3, 4, 5, and 6. This side, we're only going to take 4 of the 6 pi electrons. So we'll just do 7, 8, 9, and 10. Okay, I'm going to ignore this because it's the substituent now. So when we form bonds, okay, carbon 10 forms a bond to carbon 1. This shifts over there, shifts. 6 will bond to 7, and then shift, and that is it, right? This is going over there. So we're going to do the same thing where we're not going to form a 10-membered ring. We're going to like put 2 rings together. So what I like to do is draw one side the exact same, or you can even draw both the exact same, but we'll do like this, right? 1, 2, 3, 4, 5, and 6. And then you're trying to bond to 7, 8, 9, and 10. So ready? 1, 2, 3, 4. What the heck? 1, 2, 3, 4. Boom, you're done. This is 7, 8, 9, and 10. You get this type of structure. It looks like 2 benzenes, but you don't have this middle thing. And then just follow along where your bonds are. So 2 and 3, double bond. 4 and 5, double bond. 8 and 9, double bond. And that's it. I'm going to leave it at this. I can't really see them doing any more than that. So that's pretty much it for other pericyclic reactions that you have to know. And yeah, I just realized I forgot that. Now we're good. Let's talk about hybridization really quick, because this is kind of like a precursor to the next stuff. So when we have aromaticity and basicity of nitrogens, if you don't know hybridization, you're cooked. So let's talk. Okay, I'm going to write this out. SPPP. There's like D and stuff, but we don't look at anything past SPPP or SP3. So typical, like a regular carbon. If you look at this carbon, what is it bonded to? It's bonded to 4 things, okay? If you have like every bond or every lone pair, you're going to cross off as 1, right? So single bond, double bond, triple bond, and lone pair equals 1 each. Okay, so this carbon is bonded to 4 things, so I'm going to cross off 4. 1, 2, 3, 4. That means I have sp3. If I had this carbon, no, whatever, this carbon right here, what is it bonded to? It has to have 4 total bonds. So how many types of bonds? We have 1, 2, and 3. There's 3 electron groups. So that means I cross off spp only. I get sp2. What about C triple bond N? N has a lone pair, right? What does that mean? I have one group here and another group. Each counts as 1. So for sp3 or spp, I cross out sp and get sp. What else? Oxygen. You might be wondering how to know how many lone pairs there are. It should add up to the total valence electrons, right? So the answer is this. You have 2 lone pairs because you count each lone pair as 2 and you count each bond as 1 electron because it's shared. So oxygen is in group 6A, which means it has 6 valence electrons. So this is 2, 4, 5, and 6. So that's how you know how many lone pairs. Now that you know how many lone pairs, count the total groups. We got 1, 2, and 3. So that's sp2. So that's 3 things I'm crossing out. sp2. Okay, now. No, before that. What about this? So this is positive, right? Positive means carbon is supposed to have 4 valence electrons. Positive means that it's lacking an electron, so it has 3, okay? So it's just bonded to hydrogen. So this carbon is bonded to 3 things. There's no lone pair or anything. There's only 3 electrons. So it's bonded to 3 things, which means it's going to be sp2. What about negative? If it's negative, that means it has an extra electron. So you're bonded to H and you also have a lone pair. How many things is this? 1, 2, 3, and 4. So a negative on its own, this carbon will be sp3. But let's introduce resonance now. If you have a benzene or whatever, right? You know what? Let's just put like a double bond. If you have this and you have a negative charge, we said that a negative carbon is sp3, right? And as of right now, it looks like it's sp3 because it has a lone pair and it has an H. However, you have to consider resonance. Resonance can occur because it's allylic to a double bond. And when you do that, what is this carbon now? This carbon still has the hydrogen, but what? It has 1 group, 2 group, 3 group. That is sp2. So initially it was sp3, now it's sp2. You go with the lower one, okay? That's just what you always do. You go with the lower one. So this carbon, we cannot say it's sp3, it's sp2. Even though in this state it looks sp3, you gotta remember resonance is hybrid. It's not fully like this. So it's gonna go with the lower one, which is sp2. What about this? This negative charge is too far from the benzene or from any double bond. So this will be sp3. Okay, what about... Is this even a real molecule? I have no clue. Whatever. Nitrogen. What is nitrogen over here? So it looks like I'm bonded to 2 things. I have a lone pair. I have a lone pair and it can resonate with this. The answer is no. That's not how it works, okay? We'll explore this more later. But when the nitrogen already has a double bond, your lone pair cannot form another double bond. So you don't look at resonance at all. So this nitrogen has what? 1 group, 2 group, 3 group. It's just sp2. What about... Oh my God. Sulfur. Sulfur has 2 lone pairs. One of them can resonate, okay? One of them can resonate to give you that. And right now, it looks like it's sp3. Then it became sp2. Can you form another one? Can you do this? You cannot, because if you did that, there's 2 things that are wrong with this. Number 1, you would have a 2+ charge and... Hold on. 2+ charge and like a negative twice. So that's so many charges going on. Even if they cancel out, that's a lot of charges. Second, in a ring, you shouldn't have 2 double bonds next to each other because that is a linear thing, which makes no sense for this type of structure. So it's just not possible. So we end up with sp2, okay? So one more time, if you already have a double bond, you don't form another double bond even if it looks like it's possible. If you do not have a double bond, but you're allylic to one, then sure, you can form one. So it looked like it's sp3, but the actual answer is that the sulfur is sp2. We'll talk about one last thing. Pretend these ends had H's. Dude, I'm so cooked. Whatever. Okay, this nitrogen, the lone pair this time. What is the hybridization or what orbital is the lone pair in? If the lone pair is able to form a pi bond like that, then it's in the p orbital. However, if your nitrogen already has a double bond, okay, then the lone pair is going to be in the orbital that the nitrogen is in. So it's sp2. Sorry, I was tweaking. Okay, so this is N1 and this is N2. The lone pair on N1 is going to be in a sp2 orbital because the N already has a double bond. So this lone pair will not participate in pi bond formation. However, N2 does not have a double bond and its lone pair can resonate to form a pi bond. So that means that N2's lone pair is in a p orbital. Okay, that's all we need to know for now. I mean, that's pretty much it, but we'll talk about it more like afterwards. Okay, moving on. Aromaticity. So, aromaticity and, okay, look. So we have aromatic, we have non-aromatic, and we have anti-aromatic. This is the order for increasing stability. So aromatic is the best. Anti-aromatic is the worst. Right? Benzene is what we know for sure is aromatic just because we've been heard that since OChem 1. So when it comes to figuring out what classification things are, there's some criteria we need to look at. Number 1, is the molecule cyclic? Or at least the pi system we're looking at, is it in a cyclic structure? Number 2, right? If number 1 is good, move on to number 2. Is everything fully planar in the ring? And the way to check that is everything sp2? If you have even one thing in the ring that's sp3, you are no longer planar, and so you're just not aromatic at all. So if number 1 checks out, number 2 checks out, by the way, this implies that everything is conjugated fully, but I don't write it all the time. Okay, if number 1, number 2 are good, then you're going to either be aromatic or anti-aromatic. So now you're going to look at number of electrons, number of pi electrons. If you have 4n plus 2 electrons, you will be aromatic. If you have 4n electrons, you will be anti-aromatic. Now, n does not refer to a number that you figure out per molecule, okay? If you remember from HNMR, right? If we're looking at this H, the N is like dependent on the molecule. So over here, N is the number of adjacent carbons, hydrogens. So we have 1, 2, 3, 4, 5, 6, right? So the N over here would be 6. But then for this question, for this molecule, the N would just be 1, 2, 3. So like it changed every time. But in this case, right? In this case, N is not something you calculate per molecule. It's just like, it's an expression. And we plug in like all positive integers, including 0. And that's going to give us a set of acceptable values that if we reach these values, we will be aromatic. For anti-aromatic, it will be 4n. So I'm just saying a bunch of stuff. But let me show you what I mean. So for 4n plus 2, just plug in n equals 0, n equals 1, n equals 2, and so on. If you plug in n equals 0, you get 4 times 0 plus 2, which is 2. If you plug in 1, you get 6. If you plug in 2, you get 10. And it just keeps adding up by 4. For anti-aromatic, you can't plug in 0 because that would just be 0, and you need to have at least like 2 electrons, right? So plug in n equals 1, 2, 3, and so on. Plug in n equals 1, you get 4. Plug in 2, 8, 12, and so on. So if you have 2, 6, 10, 14, so on electrons, and you matched criteria 1 and 2, then you'll be aromatic. If you match 1 and 2, but then you end up with 4, 8, 12, so on electrons, you'll be anti-aromatic. If you're wondering, I'm going to tell you why these rules apply, but like in a second. So a big misconception or a big mistake that people do, they'll jump to number 3 and they'll just like look at the number of electrons and be like, oh, it's aromatic or anti-aromatic, but they'll completely forget about cyclic and fully planar, and they're wrong, right? Go in order. Number one, cyclic. If it's not cyclic, boom, you're done. You're non, right? If you mess up any of these, you're just non-aromatic. Okay, if cyclic is good, is it fully planar? No. Something's sp3? Okay, automatically non-aromatic. You have to match 1 and 2 before you reach number 3. So don't look at just number of electrons, because that will mess you up. Okay, so if we look at our benzene, we're going to use this as like an example so that we can understand how this stuff works. So the benzene is a cyclic molecule, right? It's a cyclic, whatever. It's literally cyclic, right? It's a ring. So that's good. Is it fully planar? Every carbon here is sp2, right? Every carbon has a double bond on it, so everything's sp2. And it's fully conjugated, right? I have double bond, single bond, double bond, single bond, double bond, and so on. So 1 and 2 are good. Now that 1 and 2 are good, we are for sure either aromatic or anti-aromatic, okay? We can't be non-aromatic at this point. We're either aro or anti-aro. We have to figure out the number of electrons. So number of pi electrons specifically, you just look at double bonds or lone pairs that are part of the conjugated system. I have 3 double bonds. So I have 3. Each double bond has 2 electrons, right, in the pi bond. So multiply by 2 and you get 6. 6 falls under the 4n plus 2 established values, which means that benzene is aromatic. All right. If we take a look at naphthalene, which is mothballs, same thing. Does it have like a cyclic structure or even like multiple? Yes. Here, I'll go back. Is it fully planar? So it seems that everything is sp2, okay? Be mindful of these central carbons because sometimes they're just not at all. But look, we have a double bond from this side, so they're going to be sp2. So everything here has a double bond, meaning everything is sp2. So we're either aromatic or anti-aromatic. What do we do now? We look at number of electrons. So all of these double bonds are in conjugation with each other, right? So you can just go like that, whatever, right? They're all conjugated. There's 5 double bonds. So 5 times 2 is 10. And that falls under 4n plus 2. So this naphthalene is going to be aromatic. And one more time, look, I get that a double bond is 4 electrons, but I'm just talking about the pi bond in the double bond. That's why we're only multiplying by 2. So we got that. Now, let's look at this example. Okay. Number 1, is it cyclic? Yes, it's cyclic. Number 2, is it all sp2? Okay, well, we got to check now. So obviously, these green carbons are sp2 because they all have double bonds. But the oxygens look like they're sp3 because we have 2 bonds and we have 2 lone pairs each, right? So that's 4 things. But we just talked about how if you have a lone pair that's 1 away from the double bond and your atom doesn't already have a double bond, then you can resonate and form a double bond. Therefore, both of our oxygens are sp2. So that means everything in this ring is sp2, right? All are sp2, which means everything is conjugated. So that's good. So now we're either aromatic or anti-aromatic. Let's count the number of electrons. Okay, so let's see if I can highlight. We have this right here. We have this, and this. Okay, notice how my oxygens have 2 lone pairs each, but I only counted 1 each. Why is this? It's because only 1 lone pair will participate in resonance. The other one is stuck in the sp2 hybridized orbital. Same thing over here. This one will participate. This one is stuck. So you don't count every single electron. You only count the electrons that are conjugated. So that means we have what? We have 2, 4, 6, and 8. We have 8 electrons. 8 pi electrons, which falls under 4n, which means that this molecule right here is anti-aromatic. Why is it not deleting? Oh my god. Anyways, let's do some more examples. All right. Let me add H over here. No, what am I doing? We'll add H right here. And then there we go, right? So let's take a look. Is it fully cyclic? Obviously. Is it fully planar or everything sp2? Yes, 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 yes. And then this one, same deal, right? It looks sp3, but this can resonate on either side. So the N is sp2. Okay. So we're either aromatic or anti-aromatic. Count the electrons that are conjugated. So double bond, and just this lone pair, okay? The N up here already has a double bond, so we don't count that lone pair. So we just count these three orange things. That's 3 times 2, which is 6, which is aromatic. If you got a molecule that looks like this, obviously there's like a portion that's not cyclic, but you don't have to say that the molecule is non-aromatic. If it has an aromatic component to it, then just prioritize that. So if they force you to give one single classification for this, just go with aromatic. But usually like the way we label these things is aromatic with non-aromatic components. That at the end of the day, like there's so many molecules out there that are not just one ring, like they have a bunch of other stuff going on, and we still call them aromatic. So don't worry about that, okay? When we're figuring out the criteria and we're talking about cyclic, just see, is there something cyclic? If there is something cyclic, then the next two steps, just focus on that cyclic thing. So over here, I have at least something cyclic. So I'm just going to ignore this non-cyclic part and see, is this ring fully planar? How many electrons does it have? And, like that. All right. This thing right here, number one, is it cyclic? Yes. Number two, is it sp2 everything? Yeah, I mean, cations are always sp2, and these are all double bonded, so yes. Number three, how many electrons? Okay, so I see that I have these two double bonds. Um, Cations do not have lone pairs, okay? So this has nothing. No lone pairs, no electrons, no nothing. It is conjugated, right? You can conjugate the double bonds and resonate and do whatever you want. But that's it, right? You're just moving the double bond around. You're not moving any other electrons. So that means we're only counting the two double bonds, which is 2 times 2, which is 4. So this molecule right here is anti-aromatic. I hate drawing rings sometimes. Wait. Okay. Let's take a look at this thing, if I can draw it properly. Okay. So number one, is it cyclic? Yes. Number two, is it fully sp2? I have no clue. Let's take a look. So sp2, sp2, sp2. This thing is also sp2 because it can resonate. But this carbon, it does not have any charge on it. It doesn't have any lone pairs. And there's no double bond. So this one's sp3. So because of this one single member of the ring, this is a no, right? So this thing is just non-aromatic. If you're done with aromatics, you can just like skip forward because I'm going to keep going. I have a lot of examples. This thing right here, number one, is it cyclic? Yes. Number two, is it fully sp2, yes, right? Double bonds, and this is sp2 by definition, so yes. Number of electrons, you just count the double bond, so that's going to be 2 pi electrons. So this is going to be aromatic, and it's interesting because number one, we finally get to see an example of there being only 2 electrons, right? So that's one thing. The second thing is, normally when we see 4 and 3 membered rings, we think of it being very unstable because of ring strain. But this is actually very, very, very stable because it ends up being aromatic. So I don't want you to think about ring strain right now. Just see. If it's aromatic, it's good. Ring strain is irrelevant. If it's not aromatic, then sure, ring strain can come in. What if we put a negative charge there? Okay, so it's cyclic, sp2 plus conjugated fully. Number 3, how many electrons? Well, we have the lone pair from here, and we have the double bond, so that's 4 things total. So this is going to be anti-aromatic. I'm almost done here. Just maybe 3, 4 more examples. Let's talk about some exceptions. So this thing is, it's fully cyclic. Everything is sp2, and it has 8 pi electrons. So you'd think anti-aromatic. However, this rule is actually violated. So everything is sp2, but it's actually not fully planar because the ring is too big. So if you have 8 or more members in a normally shaped ring that's like circular shaped, I'll explain what I mean by that. If you have 8 or more members in a ring, then you no longer have full planarity, right? It's supposed to be flat like this, but what ends up happening is it bends upwards like that. So if you're not fully planar, you're not fully two-dimensional, by definition, you cannot be anti or just regular aromatic. So this thing is violating rule 2, which means that it's non-aromatic. So when I say normally shaped ring, you might see an instance where you have something like this. This is like one continuous ring, but it's not normally shaped. It's abnormal, where you're like zigzagging, right? You're going out, then in, then out, then in, and stuff like that. This is fine. But if you have a normal shaped ring, like this is normal, where it's just like not zigzaggy. It just looks like a ring. If it looks like a normal ring and you have 8 or more members, then you're not planar. If you have something like this, then it's fine, right? In fact, the reason why it's zigzagging is to prevent any bond deviation from occurring, bond angle. So, if you look at this, what is sp2? sp2 is 120 degrees. So normally something like this is a simple 120 degrees, right? But if you have a big ring like this, then the angle is very obtuse. It's like 145 or something degrees. And we call them ideal bond angles for a reason. If it's too big, then it's just like it ruins the whole structure, compromises the integrity of the structure. So it's not good. That's why it bends upwards to relieve that strain, but no longer is planar. So this is another thing where it has a lot of members, but it already relieved its strain. And as a result, it is sp2 and fully planar. So just keep this in mind. This is abnormally shaped, but it's fine. All right. This right here, okay, we have boron. We barely see boron, but it shows up for aromatics and stuff. If you look at the periodic table, boron is the 5th element, right? You got hydrogen, helium, lithium, beryllium, boron. So boron has 3 valence electrons, and it's like the 5th element, right? So it doesn't have to fill its shell all the way. Boron is stable as is because it just needs 6. It doesn't need a full octet. And as you can see, boron has 3 bonds, so it is sp2. There's no lone pair. These are all sp2, so it's cool, right? So this molecule is cyclic, and everything is sp2. which means it's planar. But the question might be like, is it conjugated? The answer is yes, okay? Boron has 6 electrons and it's stable, but it can still take an extra 2 electrons because it has an empty p orbital. So that means you can just move this double bond like that, and you can form this resonance structure where the B has a negative charge. This would be plus, and so on, right? You can just keep it going. So this is fully conjugated, but this is the exception where it just like you don't see boron enough, right? Like you barely see it. So you have to like recognize how it works. It has a empty p orbital. It has no charge, no lone pairs or nothing, but it's still fully conjugated. Okay, so in this case, 1 and 2 are good. Now number 3 is how many electrons. As I mentioned, boron doesn't have any extra electrons, so you just count this double bond, and you have 2 electrons, which means you're aromatic. Okay. We are good. So if you're wondering like why these rules apply, cyclic, if you are conjugated, and you're like not cyclic, when you conjugate, you go this way, then you stop, then you go backwards, then you go this way and backwards, right? It's like you go, you stop, you go, you stop, and whatever. If you're cyclic, you can just keep going in the same direction and it just keeps conjugating, right? It keeps resonating. That's why you want to be cyclic. Now, for fully planar, you want to be fully planar so that your p orbitals are parallel to each other, right? When they're parallel to each other, then the electrons can flow easily. If it's 3-dimensional, then you'll have something like this, something like that, and like I don't know what orientation. It doesn't work. Okay, so that's why you have to be fully planar if you want to be properly conjugated. Now, for number of electrons, the molecular orbital diagram looks like this, where this is the lowest energy level going upwards, right? So you fill electrons 2 at a time, and you go with the lowest energy level first, right, from Aufbau's principle. So let's say you fill 2. You have every orbital with an electron full, right? So these we can ignore. There's no electrons, but this one has electrons and it's paired. So if it's paired, it's stable. If you have an unpaired electron, it's unstable. So 2 is good. What if we add 2 more? Now we got to follow Hund's principle, which means that we add it 1 at a time before filling the second, or something like that. So if you look at this, we have 2 orbitals with unpaired electrons, and we have 4 total. That's not good, which is why it's unstable. Even if it's conjugated, it's an unstable type of conjugation, making it anti-aromatic. If we add 2 more, now we have 6, right? 6 is aromatic, and it matches up because everything that has electrons is paired, and so on, right? That's why this is the set of values that we have. And that's why these are the rules. I believe I covered everything for aromatics. If I remember something, I'll mention at the end, but just to save time, let's move on. Basicity of nitrogens. So give me a moment while I draw a mega molecule. Okay, so you might be asked like rank by basicity. Okay, what does a base do? A Lewis base donates electrons. So if you want to be a good base, then you should have readily available, easily accessible electrons, because that's what a base needs to be a base. If that is not the case, then you're probably not a good base. So how do we approach this type of a question? We want to look at the hybridization or just like the orbital of the lone pair, right? I'll explain this in a second, but the first step is to find the lone pairs. So we have this. Give me one second. Let me add one more molecule or one more atom. Okay. So we want to find the presence or absence of a lone pair. So let's just draw them in. This one right here does not have a lone pair, okay? It has a positive charge, which means it's lacking an electron, and it already has octet full. So this N right here does not have electrons, which means that like it cannot be a base. This just cannot be a base because there's no electrons to donate. So off the bat, this would be rank 6. It's the worst, right? 1 is most and 6 is least. So this is rank 6. Okay, so we can ignore that. Now let's find the orbital for each of the other lone pairs. So this Cn is C triple bond N, right? This N lone pair can't resonate or anything, so it's just going to be in a hybridized orbital, which is sp. This one is sp3, right? No resonance. Over here, we do have some resonance. We can resonate this way, or we can resonate the other way. But because I can resonate and form a double bond, this lone pair is now in the p orbital. This one is also in the p orbital for the same reasons, right? It can resonate. And this one is sp2 because my N already has a double bond, so my lone pair is stuck in the hybridized orbital, okay? Now that we did this, we can start comparing. So what you need to know is that sp3 is better than sp2, is better than sp, is better than p. Let's talk about sp3 to sp. sp3 has the least s character, and sp has the most s character, right? So least s and most s. We talked about this like earlier, probably like 5 hours ago or whenever the hell I started this. We talked about this, right? Where the more s character you have, the more tightly you're held to the nucleus, right? Or the more tight your bonds are, or the more close you're held within the atom. Whereas the lower your S content is, or the S character, further from nucleus. So if you don't understand how to find S character, it's just look. There's only one S and one P. So it's 50% S, 50% P. Over here it's 1/3 S and then 1/4 S, right? So if you look at like a little nucleus, for sp3, maybe your electrons like over here. For sp, your electrons are like right here, okay? If you're held close to the nucleus and you're trying to like bond to something, like it's going to be hard because your nucleus is trying to hold you together. Whereas if you're further away, you can try pulling on this, but it's not going to be as effective. So if you want to reach something, easy to bond, okay? That's why sp3 is the best, sp2 is mid, sp is the worst out of the hybridized orbitals. So we can go ahead and start ranking. sp3 is going to be rank 1, sp2 is rank 2, and sp is rank 3. Now, we have 2 p's left, okay? First of all, why is p bad? P is bad because it's participating in resonance. Your lone pair is busy. It's busy forming double bonds and resonating. If your lone pair is busy doing other stuff, how can it act as a base and bond to something else, right? It doesn't want to because it's busy stabilizing itself from resonance. That's why P is bad in general. But when we're comparing it to another P, what is the difference here? You might think this has more resonance. That's not really the case because they both have the same number of resonance. So the distinguishing factor here is that this nitrogen is part of an aromatic ring, whereas this nitrogen is not aromatic, right? This is not cyclic, so it's just non-aromatic. This is aromatic, okay? So this lone pair is extra specially stabilized. This one is stabilized, but not like in an insanely special way. So if this is super, super, super stable and this molecule is aromatic, if it were to bond to something, then that would compromise aromaticity. It would ruin the special stability of it. Why would it want to do that? It wouldn't, right? So even though both of these P's are really low in basicity, this one is even lower than the other one. So our ultimate rank is 4 and 5. And obviously, no matter what, you cannot be as bad as this one because this does not even have a lone pair to begin with. So that is what I want you to know. One last thing on this topic. It's not about basicity anymore. I just want to make sure that we are good with the hybridization of the actual nitrogens. So remember, what we put right now in red is for the lone pairs, but in let's do like orange. In orange, we're gonna do the nitrogens, right? So this nitrogen is sp3. This nitrogen is sp2 because of resonance. This one is sp. This one is sp2. sp2 because of resonance. And this one is going to be sp3. So it's like a valid type of question. They'll ask you the N hybridization, the lone pairs, and then rank by basicity and stuff like that. Okay. I want to mention now, like before we move on to aromatic reactions, for aromaticity, now that we know about the, oh my God, I'm blinking. Oh my God, 5 a.m. What the hell? Okay, sorry. Now that we know that anti-aromatic is a thing, I don't want y'all to think of resonance automatically equaling good for what am I saying, bro? We don't want to look at resonance equals stable necessarily, right? This is not always the case. Because as you can see, if you had something anti-aromatic, then, this has resonance. This is definitely resonance. But it's not good resonance. It's very, very bad. So resonance is not always good for stability. So when we get to ranking, we're going to talk about this stuff. But don't look at just resonance, okay? Question, is this aromatic, anti-aromatic, or non-aromatic? The way to look at it is to kick your double bond up, okay? This C double bond O is not part of the ring. The C is, but the O is not, okay? So don't see, I have 4 carbons or 4 bonds or electrons and it's anti or whatever. Just follow my directions. Kick the double bond up to form this resonance structure right here. And now just look at the ring. The ring looks to be fully conjugated and stuff. It's cyclic, it's conjugated. And how many electrons? 2. So this is going to be an aromatic molecule. So you can say that this is aromatic. Some people are able to tell just by looking at it, but I like to draw the resonance structure so it's easier to see. If we had this, we can kick the double bond up and get this structure. And we can check, right? Number 1, is it fully cyclic? Yes. Number 2, is it fully planar? No, it's not because of this thing right here. So this is just not aromatic. It's not anti or aromatic. It's just straight up nothing. This one, kick up the double bond and get yourself this resonance structure. The ring itself, number 1 is good, number 2 is good. Number 3, we have only 4 electrons because positive doesn't count. So 4 equals anti-aromatic. That's our answer. All right, if I forget something, I'll mention it later, as I keep saying. Now we're going to move on to aromatic reactions, the brand new stuff. Before we begin, let's talk about one thing right before aromatic reactions. If I gave you this molecule and I said react it with 1 equivalent of MCPBA, how would we approach this? Well, MCPBA is an alkene reaction, and it reacts with double bonds and not benzenes, because we know that benzenes don't react with our old reactions. But why does it not react with the benzene? It's aromatic. So if you were to use one of these double bonds and form an epoxide, now it's no longer aromatic. It just lost its special stability. So why would it react? The answer is it wouldn't react. So the benzene is untouched. This molecule right here is non-aromatic. So it's not super stable, nor is it unstable. Of course, it is somewhat stable because of the conjugation, but it's not aromatically stable. Therefore, this is a good option. And as I mentioned, when you have one equivalent of the peroxy acid, take the most substituted double bond because it's the most electron rich, and that would be your answer. Let's take it a step further. We'll keep our benzene. We'll keep our cyclopentadiene, and I will add a cyclobutadiene. If we reacted this with MCPBA, and there's only one of them, what would we get? So this benzene is aromatic, this cyclopentadiene is non-aromatic, and the cyclobutadiene is anti-aromatic. So we're not touching the aromatic ring because it's super stable, and reacting with it would get rid of the super stableness of it. Non-aromatic is in the middle, nothing crazy, but anti-aromatic, this is super unstable, which means that if I were to react and get rid of the double bond, now it's just non-aromatic. So it's less unstable than it was before. It's better to be non-aromatic than anti-aromatic. That's why this would be our answer. Cool, now we can talk about actual aromatic reactions. Let's draw a benzene and do some quick terminology stuff. So we'll call this substituent A. So we've heard of the terms ortho, meta, and para. These are words that we use to reference a spot in relation to a given substituent. And so if we're talking about A position that is one carbon away, so we'll mark it in red, this is called ortho. If we are 2 away, now it's called meta. And if we are complete opposite side, now it's called para. So in other words, ortho is 1, 2, meta is 1, 3 positioning, and para is 1, 4 positioning. And we're going to talk more about this later, but we have certain types of substituents that want other substituents to be added in the ortho position. Some want to be in the para position, and some want them to be in the meta position. So it's good that we know what these terms mean. If we have electron donating groups, okay, so electron donating groups, for example, could be alkyl, could be an OCH3 or any OR group, OH, NH2, NHR, etc. Right? These electron donating groups, they are ortho, para directing with preference for para. So I'm not gonna give you specific reagents right now because we haven't discussed them yet. But for example, if we had an NH2 and we wanted to add just one bromine, okay, that's not the reagent. You know what? Let's just use we'll use A. If you want to add A to this is called an aniline, by the way, but this benzene with an amine, NH2 is an electron donating group, so it wants to add the A either in the ortho position or the para position. So you can get both, to be honest. So you can get this as your product, or you can get this as your product. Now the preference is for the para position, so this is more of a major product just because there's less steric hindrance. But what I'm trying to say is that you will not get this right here where it's meta. This is a no. So this might be in 70% and this will be 30%. And I'll drop this term right now. Electron donating groups are going to be activating, which means that they allow more things to be added. Like they really activate the ring, making it electron rich, right? Because benzenes are double bonds, which should be electron rich. Now, what about electron withdrawing groups? So electron withdrawing groups, for example, could be the carbonyl, could be CN, could be NO2, CF3 and stuff like that. But we'll use these for now. Honestly, we can keep CF3 here. So these are electron withdrawing. These are going to do the opposite. They're going to be meta directing. And most are deactivating, which means that they get rid of the electron richness of the double bonds in the benzene, making it less likely to react in most cases. So if we had a benzene and we put this carbonyl and we wanted to add A, the only answer we could get, at least as a major product, would be over here. Obviously I can add it on this side as well, but they're the same thing. So that's what it means by meta. Now there is one exception to this rule, the halogens. So the halogens, so F, Cl, Br, and I, these are going to be ortho para directing, but they're still deactivating. So halogens are electron withdrawing groups, but they are ortho para directing, but they still are deactivating. We can probably talk about why this is the case later, but for now, just know that this is an exception. So we'll go get rid of this. Now we can start with the actual reactions. Pay attention when I say to pay attention to the mechanisms, because there are a couple reactions where they actually ask you to draw the intermediates and stuff like that. So the first one is going to be electrophilic aromatic substitution, EAS. And yes, pay attention to the mechanism, because they love to ask this. They've asked it like 3 years in a row. So we'll take a benzene, a plain benzene right here. And we're going to introduce some electrophile that's positively charged. What happens is one of these carbons will use the pi bond to bond to the electron deficient electrophile. So we're going to bond like this. Now we formed a bond to the E. So we have this bond to the E, and we had a bond to the H, right? This has every carbon here has an H on it. So we have that. Now this carbon right here in purple just lost the double bond, right? The double bond was here between these two bonds, the two carbons, but it's gone now. So we're going to have a carbocation right here. And of course, there's still an H, but I'm just going to ignore it. Now this is important, okay? This is called an arenium ion, or arenium intermediate, or arenium cation, whatever. This is an arenium ion. And a common thing they like to do is ask you to draw all the resonance structures and indicate the major contributor. And so you can resonate like this. And get that. You can resonate again. And get that, and so on. Now, depending on what the E is, like the major contributor could change. So I'm not gonna indicate that. So it's not really a good example, but definitely know the resonance structures. Okay. I'm gonna ignore these though. I'm just gonna get rid of them. This is the intermediate. So what happens next? We have a base that's present, and the base is going to do an E2-like reaction where it takes the hydrogen and it removes this bond in the form of a pi bond. It just comes back. And what does that give us? A re-established aromatic benzene. But this time we have the electrophile added. So that's why it's called electrophilic aromatic substitution, because basically substituted like a hydrogen with an E, an electrophile, on the aromatic ring. This is the essence of electrophilic aromatic substitution, but let's talk about some examples, okay? Bromination. We're going to talk about the halogens. So bromination is the first one. Take a benzene. And we want to add bromine. But Br2 alone cannot work because the Br is not even, they're not positively charged, right? We need like an E+. So the Br is not positively charged, which is why we have a catalyst, iron 3 bromide, FeBr3. Okay, so what does this do? We're going to draw FeBr3, and we have our Br. So the iron is going to bond to one of the bromines. And when you do this, the iron becomes partial negative and the Br becomes partial positive. So this bromine does not want to be partial positive. It wants to take some electrons so that it can become neutral. So it's going to take these electrons from the other bromine, and essentially this bromine becomes a Br+. So this is our, I don't know what you call it, bromonium ion or something. It's a Br+. And we can treat it the exact same way as the E+, where one of our double bonds from the benzene will be used to form a bond to the bromine. And our intermediate would look like this. And then, you have all your resonance structures. And then ultimately, your base comes in, which I believe is going to be FeBr4 minus, but it doesn't really matter. But it's going to steal the hydrogen and reform that pi bond. And your ultimate product would be the benzene with the bromine. Now, which of these is your major contributor for resonance? It would be this one right here. Because bromine is an electron withdrawing group, and you want to be as far away as possible from electron withdrawing groups when you have a cation. So this is like the best. It's like para position to the bromine. Okay. What about this? Is called a toluene. Toluene is just a methyl benzene. So react this with Br2, FeBr3. So I'm not going to go over the mechanism now because I think we already know. But I see that we have this methyl, which is an electron donating group. And I remember that electron donating groups like ortho and para. Para is preferred. I don't remember if I mentioned this. Did I mention it? Yeah, I did. Okay. Para is preferred just because of lack of steric hindrance. So you can add it over here, or you can add it over here. It's better to add it para just because these are further away from each other. So that's what's going to happen. You're going to draw your product, and it's going to be this. Now, actually, let's talk about the mechanism because I can explain like ortho and para. So let's do this, and we'll form our cation right there. So one of our resonance structures will end up being this. Let's bring this down. This is like the best possible resonance structure you can get because our carbocation is tertiary. It doesn't matter what you have. If you had an OCH3 or an NH2 or something like that, these are all electron donating groups. So you'll be in the best position because you'll also have resonance with whatever it is. Like if it's OCH3, you have resonance with that. So the carbocation really wants to be at the tertiary position or at the position where your electron donating group is, That's why ortho and para are good. I just drew the para intermediate, but ortho will give you the same thing. If you did meta, let's take a look at the intermediate. It just like, it won't be that good. So put our, so if we added the bromine here, then the cation would be right there. And no matter how much you resonate this, you're not going to get your carbocation in the most stable position. Right? You can resonate this over here, but the cation will shift over here. So it's always going to be like secondary or something like that. That's why meta is not the best. Ortho and para are the best because you get the best, most stable rhenium intermediate. Anyways, yeah, this will be our answer right here. Okay, moving on. Honestly, we'll keep bromination. Let's do one more example. Or I'll do two more examples. So now we have CN, which is an electron withdrawing group. So I want to do meta positioning. So my answer would be a 1,3 product. So I'll draw my CN over here, and I'll keep this bromine meta. What about whatever I'm doing right now, this will apply to all the following EAS reactions. So I'll zoom through the next EAS reactions, but just spending more time on this because I'm showing different scenarios. So for this one, okay, I have an ortho para director here, and on this, I have a meta director. So I can't place something here. That's ortho, right? But I can't place something there because there's no spot for it. I could place a substituent here. That would be ortho to the methyl, and it would be meta to the CN. So that is an option. But I can also do this. This would be para to the methyl, and it would be meta to the CN. So this is ortho to the methyl and meta to the CN, whereas this one is para to the CH3 and meta to the CN. So since this is like the best, it has meta and has para, we're gonna go with that option. I should have done a different color, but we're gonna go with this option. So our product would look like that. What if we had this? There's no position that will satisfy both. So I can't do this because that is ortho to both. If I do this, that will be ortho to the OCH3 but para to the NO2. If I do this, that will be meta to both, which is not good for OCH3. And if I do this, that will be para to the OCH3, which is good, but ortho to the NO2. So there's no carbon that I can add the bromine to such that both of my substituents will be satisfied. So when a scenario like this comes up, you prioritize the activated carbon, okay? This carbon is electron, or this substituent is electron donating, and it's the activator. So you prioritize this guy. So whatever it wants, you're gonna follow that. Since we have a para position available, we're gonna do that. We're gonna add our bromine there. So our answer would be this. Okay, even though, once again, these are ortho to each other, there's nothing else I can do, so we're gonna go with that. Let's talk about a little exception type thing. I don't really know if it's called an exception, but like an interesting scenario. So if we have this phenol, the OH is electron donating, and it's a pretty strong electron donor or electron donating group. So as a result, this benzene is actually really activated. Okay, once again, activated meaning like it likes to react. It's able to react easily compared to if it was deactivated. So if you were to bring in Br2 FeBr3, this is actually going to react as many times as it can, meaning it's going to polybrominate. So at first, you would add your bromine to the para position, but you're also going to add it to the 2 ortho positions that are available. This is called polybromination. Definitely know this because they like to ask this as well. What if I don't want to add all of those bromines? This time you can use Br2 without a catalyst. This will just add it one time. So you'll get OH and Br. Or you can do the ortho version, which will be there in smaller amounts. So OH and Br. So catalyst plus activated ring equals polybromination. Super activated ring. So super activated, usually you're going to see either an OH or an NH2. Methyl is not enough, okay? If you had this and you reacted with Br2, FeBr3, you're not going to get 3 bromines. You're just going to get 1 because the methyl, although it's activating, it's not activating enough. So you should have an O or an N for this to occur. I think y'all will know the answer to this one, but what if we have 2 electron donating groups and only one of them can satisfy their directing requirements? Right, so for the OCH3, neither of these substituents have a para group available because these are para to each other. So I can only place my substituent ortho to the OCH3, which would mean that it's meta to this methyl, or I can do ortho to the methyl, which would be meta to the OCH3. So what do I do in this case? In this case, just take the more activating substituent or the stronger one. It should be obvious, right? Like oxygen is going to be stronger than carbon, so oxygen will be the more activating one. If you had nitrogen, nitrogen should be the best, I believe, but usually it's comparing a non-carbon to a carbon. So since OCH3 is stronger than carbon, you're going to favor the OCH3. So we're going to place the substituent ortho to the OCH3, putting it right here. And actually in this case you can have polybromination, but like if we didn't have the catalyst, then we can just add 1 like that. All right. Now we can zoom to the next couple. So chlorination, I'll just I'll just mention the reagent. The reagent is going to be Cl2, and this time aluminum 3, or just aluminum chloride. So AlCl3, for the same reason this will work, right? So you have AlCl3, and then you have a ClCl. So it bonds to the Al, you get negative, positive, this breaks off, Cl plus, and then you get your product. So I already went over the full details in the previous thing, so we're not going to spend too much time, but you get that. And if you did, if you had an activated ring, so an aniline, and you reacted with the Cl2 AlCl3, then you'll polychlorinate. Simple as that. moving on, we have iodination, which just means you're adding an iodine. For this one, the reagent is going to be I2 and HNO3. So same thing, right? An I plus will be formed, and you add, through electrophilic aromatic substitution, you add the iodine. Now, what about fluorination? What about fluorination? Fluorination, you actually, like, it's really hard to form an F plus. So you're not going to do what we did for the previous three. Instead, we're going to do something a little different. Let's fill this in. So we're going to start with an NH2. And if we react with NaNO2, this is a pretty important reaction to know. You form what's called a diazonium salt, right? Diazonium salt. And this thing is a very good leaving group because when it leaves, it's just N2 gas, which is neutral and stable. So I'm not going to get into the full mechanism, but essentially you're going to use HBF4 and once again, without getting into the full mechanism, I'll give you a very simplified explanation. You're going to have like a BF4 minus. Let me see if I can, here, 1 second. And like this thing will leave. And you're going to have like a plus in the benzene, and it wants to get rid of the plus by bonding to something. So it's going to snatch a fluorine and make BF3, right? So then you end up with the fluorine on the benzene. I hope that made sense, but this was like a very like simplified explanation. Honestly, these mechanisms don't matter, right? 1 second. The only mechanism that you need to know is the electrophilic aromatic substitution and the whole AlCl3 thing, like how that works. But this one doesn't matter. I'm just trying to explain. But essentially, you're going to just swap the N2 with the fluorine. So this is how you add a fluorine to the benzene. Because you cannot just make a F plus with like AlF3 or something. It doesn't work like that. All right. By the way, you can, if you're probably wondering, like, can you replace this with other things? You can. Usually things with copper. So like if you had copper cyanide or like CuI or something, these will act as nucleophiles and do a mechanism like this. Just keep in mind, this is not really SN2 or SN1, but for simplicity, we can think of it like that. But the copper is there, and you can't just use like a regular nucleophile. You need the copper because it allows like radical transfer and stuff that's involved in the mechanism. Don't worry too much about it. But let me show you what I mean. If we had this and we react with CuCN, our product would be the benzene but with the Cn instead of the N2. So you can do that. I think this is called the Sandmeyer reaction. Cool, let's move on. Let's talk about nitration. How do we nitrate a ring? So we'll take our benzene and we're gonna do HNO3 H2SO4. Essentially, like when you have HNO3 plus H2SO4, you get NO2 plus HSO4 minus plus H2O. This NO2 thing looks like this. So this is another example of an E plus, right? Your electrophile that's positively charged. So for that reason, we can say that we add the NO2 onto here, which looks like this. But you can just write it as NO2. What if we wanted to add an NH2? So we can't directly add an NH2 as far as I'm aware. So what you can do is add the NO2 and take it a step further and use a reducing agent like H2PDC, or another common one is going to be like zinc HCl, or like tin with HCl, or like another metal like FeHCl, right? This thing right here, by the way, especially the zinc, we're gonna like come back to it again. It's called Clemmensen reduction, but you can use any of these, and it's going to give you NH2, which once again is called an aniline. I forgot if it has one or two L's, but that's what it is. So you cannot add an NH2 on its own. You have to go from NO2 to the NH2. Moving on. Talk about sulfonation. So we're trying to add an SO3H group. So we have our benzene. Pretty simple stuff. You're just adding your SO3H. If you're wondering, this thing is deactivating, so it's going to be meta directing. Okay, moving on. What if we want to add an alcohol to make a phenol? So this is another instance of where you can't do it directly. You're going to take this SO3H and you're going to react with, I believe it's going to be just like NaOH. It's NaOH, and there might be like workup steps and whatever, but you can just say NaOH and heat, and that will give you OH. So SO3H was deactivating, but OH is activating. So that's like a little trick you can use if needed to switch the whole chemistry of the benzene. But yeah. We are done with the electrophil. I mean, not really, but like for like adding adding like fluorines and stuff like that. Another thing we can use, or another type of reaction, is called Friedel-Crafts. And there's two things. So we'll start with alkylation. The other one is acylation. So we'll just do ethyl chloride. You're going to have some sort of alkyl halide. Usually it's an alkyl chloride. And you're going to bring in the AlCl3 again, the catalyst. And this is important because you're trying to form a cation, right? So if you have your AlCl3 and you have your ethyl chloride, the Al will bond to the Cl. And it's the same deal, right? Where your Al is partial negative and the chlorine is partial positive. So you're going to break off this bond and you end up with this, right? A carbocation. And this is yet again another example of an E+. And so you're going to add in your ethyl to your benzene. And you get that. Definitely know this, by the way. Know this mechanism. Now, an issue, I don't know if it's an issue. I mean, it could be an issue depending on what you're doing, or it could be low-key helpful. We have a carbocation, right? So over here, we don't see anything. But what if we're reacting with this? Chloropropane. We're going to have our benzene plus this right here. This is a carbocation that's primary. What do carbocations do? They rearrange. So it's actually going to move up here. And your product will reflect that. You're going to have a benzene with an isopropyl instead of an N-propyl. So you're not going to get this product I'm drawing at the bottom. This is not going to happen with this reagent. This would be your product. So essentially, like any carbon chain that's longer than 2 carbons is going to be like an iso version, where it's going to be bonded to a secondary carbon or something like that. So keep that in mind. If you're told to go from here to here, you can't do the Friedel-Crafts alkylation. You're going to have to do the acylation and reduce it, which we'll talk about afterwards. But essentially, this reaction is forming carbocations that are going to be our electron or electrophiles. Another type of reaction you might see is this. So HF is a weak acid. It's actually kind of important that we're using a weak acid because weak acids dissociate a little bit, but not too much. Okay, so you have an H plus and F minus, and the H plus will allow us to form our carbocation, but the F minus is a very bad nucleophile. So we're actually not gonna react this and get that. So what does this mean? This is fully there, like it's stuck as a carbocation because the fluorine can't attack it. So that's where the benzene comes in. Now, if we have our benzene, this is an E plus, and this is our benzene. So we can just attach it. So your benzene will have the isopropyl group on it. So like, once again, if you did HCl and step 2 was benzene, the issue is that you'd probably just have this, and now you don't really have an electrophile. So that's why you usually use something like HF, where you don't risk a substitution occurring. Another interesting one that we haven't really seen before is reacting in alcohol with BF3. So this thing, it's kind of like tosylation, where it's gonna make your alcohol into a good leaving group. But this is a stable leaving group, so it's going to just get rid of it and form your carbocation. And there's nothing here to get rid of this charge. So if you bring in a benzene, it will just attach to it and form your isopropyl. So yeah, that's pretty much it. Okay, if I gave you this, draw the intermediate first, right? The carbocation. So when the chlorine leaves, you would get a secondary. And then you're going to rearrange it to the tertiary position. So your real intermediate is this. And then your benzene comes in and attaches to that. So you're going to get this, right? To make it easy, we can like number it like 1, 2, 3. So we're bonded to carbon 1, 2, 3. And then carbon 1 has this. So that would be our answer. What if we react this with 2 equivalents? The first time around, you'll get 1 over here. And the second time around, we're going to do ortho-para directing, right? So we add it to the para position because that's available. If I have this molecule and I want to react what would I do here? So previously we talked about how like the stronger activating group would be prioritized when choosing ortho-para stuff. Over here, these are both like alkyls. You could make the argument that this is more activating just because it's more electron donating. But the issue here is that this is pretty bulky. And so if you were to add a substituent here, there would be a lot of steric hindrance. So in this case, you would actually prioritize the smaller one. Okay, when you're dealing with just carbons, prioritize the smaller one. So your product here would be tert-butyl on top, methyl here, and then isopropyl down there. And why did I do an isopropyl? Because we form this as our intermediate and it rearranges to the secondary position. Question. what would the product of this be? The answer is no reaction. So we talked, I dropped the terms activating and deactivating. This is an example of like a type of reaction where if you're super deactivated, you're just not going to work. Okay, because E plus, this depends on your benzene being pretty electron rich. And when you have all these electron withdrawing groups, they're withdrawing the electron density, which means that your double bonds are not as electron rich. So you're not really able to react properly. Okay? So the general rule of thumb is like if you have I think like 2 withdrawing groups, then you're deactivated. I don't really think that they're going to give you an example of no reaction occurring, but what you will have to do is they'll give you a benzene and they want you to make a product that has like A, B, C, all these things. And you have to figure out the order, right? Maybe you want to add A first, then B, then C, or maybe you want to add B first, then A, then C, and stuff like that. What you want to be careful of is to not deactivate your ring too much when you're not even done, because they'll take off points and say like this ring is too deactivated to occur. But as far as them giving you a question and the answer is no reaction, they're not going to do that. They usually don't do that. So I just want you to keep this in mind though. And I'll give you more examples when we do like synthesis probably, once I forget. Okay, we have graduated from Friedel-Crafts alkylation. Now we're going to move on to Friedel-Crafts acylation. So this one's a little similar. I mean, I hope y'all are noticing how repetitive these reactions are. Like the whole chlorination, iodination, bromination was repetitive. This whole concept of electrophilic aromatic substitution is repetitive as a whole. It's just a matter of remembering the reagents, but the reagents are also just giveaways. Like they have the thing in there, right? The substituent that you're trying to add. So it's really not that bad. Okay. We're trying to add this guy. So the product of this would be that. Same exact deal, right? This chlorine is bonding to the Al and it just breaks off. So you're going to get this as your intermediate, or you can even look at it like this. I forgot what it's called. I think it's like acylium or something. But this is your intermediate. And for the 59,000th time, this is an E+, and so your benzene will just attach to it. So that's what we get over here. Okay, what about that? Our product would look like this. Notice how there's no rearrangement and stuff like that. We formed a plus over here and I kept it there because it's not going to rearrange from that position because it's already stabilized by the oxygen. So it stays like this. Now this is important because we can take it a step further and turn it into that N-alkyl chain. N meaning like it's a straight chain. It's not iso or anything like that. We can do this. All you got to do is reduce it. So if you use, there's 2 types of reductions, right? One of them is called Clemmensen reduction, and this is going to be acidic conditions. So the reagents we use here is going to be Zn amalgam HCl. You can also use like the SN HCl, Zn HCl, Fe HCl, right? All of these have the HCl in it, which shows that it's acidic and it has some sort of metal. So you can use these, right? This is Clemmensen reduction, or you can do Wolff-Kishner reduction, which is going to be basic. Now Wolff-Kishner is going to be NH2 and some sort of base, so like KOH or NaOH. Right? This shows that it's basic. Both of these will give you the exact same outcome. So you can use ZnHCl, or you can use NH2, and base. So remember, we cannot achieve this from that. Because what would actually happen? You would get a rearrangement where it would be over here. And so your product would actually look like that. So if you ever get a chain that's longer than 2, like a straight chain that you need to add, you would have to do a Friedel-Crafts acylation and reduce it. Now, you might be wondering, I don't know if you're wondering, hopefully you're wondering, let's say you have an NO2 and this. If we just want to reduce this acyl group and not the NO2, like, how does that work? So if you use the ZN HCl, you're going to reduce both, and so you would get that. But if you want to keep the NO2, then you can use Wolff-Kishner, which is NH2, NH2, and KOH. So that would give you NO2 is intact, and then that. So we can keep that in mind. Let's move on to Birch reduction. So Birch reduction is finally an instance of getting rid of a double bond on the benzene, like for good. Like you're just straight up reducing the benzene ring, which we've never seen before. So let's take this, right? We've got a benzene with some substituent on it, and in particular it's electron withdrawing. The reagent is going to be NaNH3 liquid, right? I think y'all might remember this, that when you had an alkyne and you reacted with Na and sodium ammonia, it gave you a transalkene. It would give you this, right? A transalkene. So it's a reducing agent. So we're bringing it back. And usually you're going to have like an alcohol as your solvent, like methanol. Now, I'm not going to go over like the full mechanism, but an intermediate that you receive is this. We're going to get a radical and then a negative charge. So in this case, if our negative charge is the most stable, we'll keep it like this and we'll get rid of our charges and we'll neutralize it. But if it is not stable, then we're going to have to do some resonance and stuff like that. So in this case, it looks like my negative charge, it's tertiary actually, and it's stabilized by this electron withdrawing group. It can do resonance with that. So we're going to keep it like this, and our answer is going to be that. But then if we bring in, what do we do? OCH3. OCH3 is electron donating. So, what was it, like this, right? This is not the most ideal because our negative, has an electron donating group with it. And you can't even resonate with that. So it's not ideal, right? You want to be away from electron donating groups. So if you draw a different version of this, this is better because your negative charge is away from the donating group, right? This is just a regular secondary. You can also draw this. This is even better because it's like further away, right? This one was 1 away. This one is 2 away. And then if we take it a step further, actually I think that's it. Am I tripping? Hold up. So I'm actually tricking you though. You can't do this because just think of it like this. You're able to swap these two, right? You're able to swap the negative and the radical. So this is actually not a legit thing, which is why you're going to ignore this. So the furthest you can get is something like this. And it actually is identical to this for the reason I just said. You can just like swap the location of the negative and the radical. So that thing is essentially the same thing as this. I'm purposely not like doing resonance and stuff just to like save y'all from confusion. So anyways, what I'm trying to say is that your product for the electron donating group would look like this, where you have a double bond on that carbon that has the electron donating group on it. Whereas for the electron withdrawing group, you're going to have it away from it. So EWG, Birch reduction, will give you EWG like that. And then electron donating group, you do Birch reduction, something like this, right? It doesn't matter if it's like this or if it's like that. As long as you have a double bond like on this carbon that has an EDG, it's fine because they're all the same. This is not the same because you don't have a double bond on this EDG or EWG carbon. So that's the only difference. But as long as you have the double bond on the carbon with the EDG, then it's correct. And as long as you don't have a double bond on the EWG carbon, then that one will be correct. Now we're going to do my favorite reaction. Side chain oxidation of the benzenes. This is where we get to add carboxylic acids. So let's take a look at this. If we react with KMnO4, right? KMnO4 is an oxidizing agent. We're going to end up with that carboxylic acid. If we do an ethyl with KMnO4, we'll still end up with the carboxylic acid of the same length. If we do that with KMnO4, we still end up with the exact same product. Okay, if I reacted this with KMnO4, my product would look like this. So as you might have noticed, this terbutyl did not become a carboxylic acid, but everything else did. The only criteria that has to be met is that the carbon that's directly bonded to the benzene has to have at least one hydrogen. If it has at least one hydrogen, then the rest of the chain does not matter. It will get cleaved off and turn into a carboxylic acid. So over here, this has at least one hydrogen, so we cleave off all of this and just turn this into a carboxylic acid. Over here, we have some hydrogens, so there's nothing to cleave off here, but this becomes a carboxylic acid. This thing has at least one hydrogen, so it doesn't matter. We cleave off everything and turn it into a carboxylic acid. Over here, this carbon has no hydrogens, so there's nothing to cleave, and it just stays as is. That's why our answer looks like this. What if we had this and we reacted with KMNO4? Take a look at your directly bonded carbons. We have this one and this one. They both match the criteria. So what you can do is cleave and cleave, right? So we're going to completely get rid of this right side. So we'll get rid of this and turn them into carboxylic acids. So that's what we get, carboxylic acid. That is our answer. What if I have this? Now what do I do? So let's take a look. This carbon is good, right? It has a hydrogen, but this top one in pink is not good. So we're only going to cleave the green carbon. So we're going to cleave the bond next to it. And we're going to separate. We'll push this that way and this way. So we'll draw our benzene. And we'll turn this carbon 1 into a carboxylic acid. Right, this is carbon 1. But what happens to the rest, right? Carbon 2, carbon 3, carbon 4. It stays, right? It's just like it detached from carbon 1, right? Carbon 1 and carbon 2 are no longer bonded, but this whole thing is still bonded to the benzene from the other side. So we'll keep it as is, right? So carbon 4, carbon 3, carbon 2. This is 4, 3, and 2. But we're actually not done. Carbon 2 is also going to be a carboxylic acid. In our previous examples, when we were looking at something like this, all we cared about was like the benzene product. We don't really care about the byproducts. So we were like, okay, we'll just cleave this and turn it into a carboxylic acid. But technically what happens, you're separating both and both sides are being oxidized. That's how KMNO4 works. So technically in this, you're making two products. One is that and the other is this. It's just that we focus on the benzene product. That's why we never look at the other thing. But you are absolutely forming two carboxylic acids every time you cleave one time. So in this case, 1 and 2 are both being turned into carboxylic acids and they're cleaved off from each other. It's kind of like this. Y'all might remember this reaction, right? When you cleaved it with like O3, you separate them, but they're both being oxidized. So one of them would become an aldehyde and the other one would be a formaldehyde. But sometimes we only draw one of the products, but they're still both being oxidized. So that's what's happening here. So this is our answer. We'll do one last one. But like at this point, there's not much I can do to trick you because we already like know everything now. So yeah. I think we'll do that. Okay, if we react this with KMNO4, just take a look. So this carbon is good. It's just going to cleave off both of those. So we're going to make a benzene. Top is going to be a carboxylic acid. This thing is also good. It has at least one hydrogen. So this becomes into a carboxylic acid. Now we can go ahead and number this, right? 1, 2, 3, 4. We're going to cleave between 1 and 2. We're also just going to get rid of this thing entirely. We're just going to get rid of that. So carbon 1 will turn into a COOH, right? This is carbon 1. And then on the other side, we have 4, 3, 2. So this is carbon 4, 3, and 2. And 2 became a carboxylic acid. So, and don't forget the chlorine on carbon 3. So you got that. That is our answer. Not yet. We forgot this thing right here. Okay, someone might be like, what do you do here? This has a hydrogen, but it has a double bond. What do we do? don't think too deep, right? This is an aldehyde. KMNO4, it's, yes, it cleaves and stuff, but it's still an oxidizing agent. So like you can just oxidize an aldehyde into carboxylic acid. There's no need to cleave or anything. So all you're doing is just oxidizing it. I hope that made sense. So you would add a carboxylic acid right here, and you're done. Okay, let's move on. So now we're going to talk about nucleophilic. I'm not going to write it out. It's called nucleophilic aromatic substitution, so NAS. So we had EAS, now we're doing NAS. So finally, we're actually able to react with the nucleophile, like straight up, like SN2, but we're not going to do SN2, okay? Please don't do SN2, but it's going to be like SN2. So let's do this benzene, and we have a chlorine that we want to replace with NaCN. Nothing will happen here. This can't work because this is an OG reaction, right? Where we just attack this, kick it off. We can't do that because the benzene ring is a benzene, it's sp2. However, if you did want to do this, you would have to have an electron withdrawing, or like a deactivating group. Okay, you need a deactivating group present. Now, if you bring in NaCN, your answer would be that substitution. But I want to emphasize this is not SN2. I'll briefly go over the mechanism, but you don't need to know this. But like essentially you attack this, and then you kick off this bond right here, and then you bring this, I need to draw NO2 actually. What the heck? Sorry. Let me draw what NO2 looks like. Okay, so you kick off this bond into a double bond, and you kick this up. And so your intermediate will look like this, where you have the CN and the CL. They're still attached. And you got a double bond here, and now you have a double bond like this to the N, and both O's are negative. Then what happens is one of your oxygens will reform the... Oh my god, I think my Apple Pencil died. Okay, I'm using my finger. So this will reform the pi bond, kick this down, and then kick the chlorine off. And you ultimately end up with that product that we had. So we have NO2, we have our benzene, and we have our CN. And for this reason, you need to have a deactivating group that's electron withdrawing, and you need to have them placed in either the ortho or para position. Okay? I'm not going to draw out all of the options, but we showed the para version. The para version allows this whole chain reaction to occur, right? Up here, where it goes all the way up and then comes all the way down. The same thing will happen with ortho. But if you're meta, this will not happen. So you need to be ortho or para electron withdrawing group. This has nothing to do with how NO2 wants things to be meta. That's not what I'm saying. You want your leaving group to have the electron withdrawing group placed ortho or para to it. So if I had this and I reacted with NaOCH3, this is fine because my NO2 is ortho to my leaving group. So my answer would be this. Now, something new that you would never expect is that fluorine can actually be a leaving group here. So if I had this, and I reacted it with NaOCH2CH3, fluorine will actually be a leaving group. Because remember, this is not an SN2 type mechanism. This is different. So whatever you learned from SN2 and SN1, it doesn't apply here. Fluorine would be a good leaving group, and your answer would be a substitution. And both of my electron withdrawing deactivating groups here are ortho and para, so that works. Now it's interesting because normally we talk about needing rings to be activated, and deactivation is bad. Deactivation is bad for electrophilic aromatic substitution because what is going on? You have a benzene ring and your double bonds are attacking things, okay? Which means that this has to be electron rich. The reason we call something like CN or NO2 deactivating is because they pull electron density away. That means you can't react properly. But what is going on in nucleophilic aromatic substitution is the opposite. This time, your benzene is acting like a plus and it's accepting electrons. So if you have things that are electron withdrawing, they're pulling away electron density and further positivifying your benzene ring or whatever double bond. That's why you want something deactivating. I don't even want to use the term deactivating anymore because it sounds wrong here. But you just want something electron withdrawing for a nucleophilic aromatic substitution to occur. So one more time, remember that you cannot react like this. This will be a no reaction. You have to have at least one electron withdrawing group and it has to be ortho or para. And then now we can say that it reacts. We are almost done with the aromatic reactions. So let's get rid of all of this stuff. We're going to talk about some fun stuff, okay? There's 3 more reactions I want to talk about. They all pretty much do the same thing. They're just like different set of reagents. But let's talk real quick. This is a Grignard reagent. And we know that a Grignard reagent is essentially a negative carbon. But we cannot react like this and say, oh, SN2, okay, I have this formed. That does not work, okay? Grignards do not react with alkyl halides. They only react with carbonyls and epoxides. This does not work because the Mg makes this a very, very, very strong base. So, of course, this is a strong nucleophile, but it's also a super strong base. So, a very big risk and something that happens most of the time is elimination or some sort of coupling that you don't know about and can't really comprehend. So, I won't get to that. But you won't ever get an SN2 type reaction with MgBr. But if you want to do this exact type of reaction, you're going to have to use organocuprates. You might have heard of them as Gilman reagents. So this is like MgBr, except you're going to use Cu and some metal like Li, or not, yeah, whatever, Cu Li. And usually it's going to be like this, where you have 2 of them. So a common depiction of this is that essentially it's just like 2 of the same groups on the Cu, and it makes it positive and this is negative. Oh, backwards. Oh my god, I'm so cooked. This is positive and this is negative. Doesn't matter. But you're gonna have 2 of these. So now if you react this with let's do that. The way you can think about it, just take one of these, okay? Take one of these, make it negative, and then do a regular SN2 where you attack this carbon and you kick that off. And this is your answer right here. You added 2 carbons. I'll highlight them. You added these 2 carbons. So this is what we always wanted to do, but we weren't able to do it because we didn't have the right reagents with us. So what you gotta do is CuLi. This is a new type of MgBr. It's CuLi. It's a Gilman reagent. So you can do that. Now, a very cool thing about this is you can actually attack sp2 carbons now. This is insane. You can attack like a benzene straight up. So let me give you an example. I'll make a benzyl bromide and I'm going to react with CuLi. How do we approach this? Draw out your alkyl halide again, and then take one of these Gilman reagents. So we're going to do just one of the benzenes and put a negative charge on one of the carbons. And just pretend like you're doing SN2. Attack this and kick that off. And your ultimate product is two benzenes bonded to each other. That is insane. Like, we were never able to do this. Now we can do it. And as you might have noticed, I made my nucleophile sp2 as well. So that's cool. We'll give one more example and then we can move on. So again, rewrite this Gilman reagent. I'll do it in green. Just draw one, right? Whatever's in the parentheses, just draw one of them and make it like negative. And then bring in your substrate, which is this thing right here, and attack the carbon that has the halide on it. So you attack this and kick this off. And you can draw your initial thing as it was. So it was like this, right? And we're adding two carbons, the green carbons, right? So we're going to add 1, 2. And these carbons are still double bonded. So you made this. This is your product. That is so cool. We're finally using a carbon as a nucleophile to attack alkyl halides. And on top of that, we're able to just straight up attack vinylic and aryl carbons. So that is amazing. So this was called Gilman. Now, yeah, the next two reactions are like the same thing, but just different reagents you have to use. So it's also called the what the heck reaction. This one, let's draw our halide. You're going to just straight up draw the thing that you want to attach to it. And under it, like the other reagents involved are going to be palladium with acetate and then like a triethylamine. Right, this thing right here, this PD and the ET stuff are always there. That's, if you see this, you know it's a what the heck reaction, and you know it's going to do like a carbon-carbon bond formation with double bonds and stuff like that. So what is your answer? Draw your alkyl halide as it was, remove the bromine and attach this thing, but keep in mind you're attaching from the double bonded side. Okay, you have to attach from the double bonded side. So you're going to bond like this. So carbon 1, 2, 3. So 1, 2, 3. 1, 2, 3. And you have a double bond right here. So I guess a difference you can figure out between this and Gilman so far. Gilman, obviously you have the CuLi stuff, right? But for Gilman, you don't have to be bonding from a double bonded carbon. Like in this case, we just have regular sp3 carbons, right? We don't have to bond from a double bonded side. This one, you have to bond from a double bonded side, right? You have two options. You could have either bonded this one or this one in the square, but the answer is the square one. That's just how this reaction works. Another example, we'll use like the same one as the previous set of reagents. Okay, let's say I want to react this with that, and I have my PD thing, right? PDOAC2, ET3N. I'm going to keep this as it is, so I'll draw that. Okay, and I want to bond to this. Now you're going to bond to the free side. So you do have two options here. You could bond here or here, but you want to bond to the, I guess you can call this like a primary carbon. You bond to the primary side. So you're going to bond 1, 2, 1, 2, CN. So that's your answer. Cool stuff. And the last one is going to be called Suzuki coupling. So it's kind of like the Heck reaction, except just different reagents, right? So like, what do we got? I think it's, okay, we'll just draw like a benzene. And okay, this is what you have to know, right? To know it's a Suzuki coupling, basically the attacking molecule, like the nucleophile, will be bonded to a boron that either is bonded to two alcohols or to two R groups. So it could look like this, where it's a boron bonded to two OR groups, alkoxy groups. So you have that for sure. And at the bottom, you're going to have PD again. So like PD, I think it's PH3, 4, K2CO3, something like that. Something like this. You're going to have this. Now, how do we approach this? Okay, look. First of all, your boron thing has to be bonded to an sp2 carbon. And so this sp2 carbon is the attacking nucleophile. And obviously, the one that gets attacked is the one with the alkyl halide. So you're going to attack like that. So we'll keep our benzene in light purple as it was, and we're going to attach this thing. So we completely get rid of the BOH stuff. So we're bonding to the benzene. If we take this, we'll use the OR this time. Let's take this as another example. PD, P, PH3, 4, NaOH. Yeah, I remember now. You can use NaOH or K2, some sort of base, right? So, same deal. We're going to draw our green molecule again in green without the iodine. And we're going to attach everything else from the boron. And this will be our attacking molecule. So you have to attach it from that side. So we're going to add it. So you have 3 carbons, right? 1, 2, 3. And we have our double bond there. Okay, I think we are good. One more time. I keep saying one more time, but I believe that Suzuki and Heck have to be like the primary sp2 carbons. So that's why we, when we had this example, we didn't bond from this side, we bonded from the other side. Cool. So we're done with aromatics, but I actually want to add in another topic about naphthalenes. Naphthalenes are very, I wouldn't say uncommon, but if they ask you, it's like a small set of questions or just like even one question. So this is a naphthalene. When you have a naphthalene and you wanted to add something like Br2 FeBr3, just add it like you normally would, right? Over here it doesn't really matter because it's just like 2 benzenes together. So actually it does matter. Yeah, it does. Okay, so we'll keep this. Where do we add our bromine? Because the question comes up because we can add it here in red or we can add it here in orange. Same thing for the other side, right? All the reds are the same and all the oranges are the same. So the red positions, I'm not going to get into mechanisms because you don't need to know the mechanisms, but the red, I'll call it like the alpha carbon, and then the orange, I'll call it beta. The major product is going to be the alpha. So that's it, right? We're just going to add our bromine right here. That is our answer. That's our major product. If you did the other one where you add it over here, it's a minor product, it's fine, whatever. Let's do another question. Next example, we'll do I2HNO3. So the rule of thumb is you add to the A position or alpha of the more activated ring. So we have 2 rings over here. The more activated one is the left side because this is electron donating. It's an activating group. And we only have 1 alpha position available. It's this one. So we'll just add it there. That will be your answer. So you can draw this again. The mothball, OCH3, and iodine right here. That is our answer. Now what? We'll do what? Let's do Cl2, AlCl3. We want to add to this. So the more activated ring is the right side, but we have 2 alpha positions available. So which one do we do? I think it should be pretty obvious, just like from logic, but you're going to keep it as far away as possible from the NO2. Maybe it's not obvious, but it has to do with the intermediate, which I purposely didn't show. But just keep it as far away as possible. As long as it's on the 1 position, you're good. So those are like the 3 scenarios I can think of happening when it comes to naphthalenes. But that's really it for aromatic reactions. I hope I didn't forget anything, but I think we're good. We're going to get into some ranking now, common ranking questions. Let's try to speed run this. So the first one is asking us to react with the Friedel-Crafts alkylation reagents. And this question, like, it's written like this, but keep in mind that this is referring to anything that's electrophilic aromatic substitution. So they may not write it like this, CH3Cl in Friedel-Crafts, whatever. They might just say rank by reactivity in an electrophilic aromatic substitution. The ranking will be the same, but I'm using this as my example. So if we remember Friedel-Crafts or just any electrophilic aromatic substitution, we are looking for activated rings by electron donating groups. That's going to be good for us. Next in line would be nothing, and the worst would be electron withdrawing groups, which deactivate. So we'll keep that in mind. Let's start with like the benzene. Benzene is nothing, so I'll not write anything. For this one, I see that we have 2 electron withdrawing groups. We have electron withdrawing group. That's probably going to be really bad, but we don't know if it's the worst yet. I see a deactivating bromine. Over here, I have 2 electron donating groups. By the way, let's just put this as EWG. And over here, I have 1 electron donating group. Okay. So rank 1 will be this one right here because it has 2 electron donating groups. Rank 2 will be this because it has 1 electron donating group. Rank 3 will be the benzene because it has nothing, which is better than having electron withdrawing groups. This molecule will be 4 because it has 1 withdrawing group, and this will be rank 5 because it has the most electron withdrawing groups. And once again, the more electron withdrawing groups, the more deactivated, so less likely you are to react. The more donating groups, the more activated you are, and the more likely you are to react. So this is our answer for the first one. The next one we've talked about already, but I'm bringing it up again. We're ranking by the lambda max in a UV vis. So remember, more conjugation equals higher lambda max. So we're just going to find how many double bonds are in conjugation. Let's see, over here I have double bond, and it ends at that. So I'll put 2 double bonds in conjugation. Over here I have double bond, single bond, double bond, single bond, double bond. That's 3 double bonds in conjugation. Oh shoot, oh no, 1, 2. I have 3 double bonds in conjugation again, so I have to figure out like a little tiebreaker there. And over here, I don't have any double bonds in conjugation, so I'll put 0 double bonds. So I know for sure that rank, what color am I using? Let's use this. Rank 4 will be this because there's no conjugation. And rank 3 will be this one because it has the medium or median amount of conjugation, right? It's less than 3, but it's better than 0. So now over here, I have to do a little tiebreaker. Hold on. No. Whatever, I'll just leave it there. I have to do a little tiebreaker, and the number of double bonds of conjugation is the same. So now we're going to look at just alkene stability. So that means that we have to look at number of substituents per double bond first, okay? No cis and trans, just number of substituents. So over here, this is 1, okay? So I'm going to I'll put a 4 next to it for tetrasubstituted. This one is 1, 2, 3, 4. This is also tetrasubstituted, and this one is 1, 2, 3, 4. So all these are tetrasubstituted. That's probably going to be the best because how do you beat that? Over here, this double bond is 1, 2 tri-substituted. This one over here is going to be tri-substituted, and whatever, right? It's clearly not 4, 4, and 4. So our most stable or best looking molecule will be that one, and this will be number 2. So remember, more conjugation is the best, but once that's the same, then you look at stability of the double bonds. All right, moving on. Rank by reactivity with a common dienophile. So this is something that I said I was going to talk about, but I actually didn't. And let's go back to Diels-Alder, right? So Diels-Alder, you have to be in an S-cis conformation in order to react. If you're in an S-trans conformation, you won't react like this. You would have to rotate yourself, become S-cis, and then you can react. So knowing that, we automatically rank this as 5 because this is S-trans, right? And it cannot just rotate because it's stuck in a ring shape, which means that this will not react at all. Likewise, this is going to be, or not likewise, but opposite. This will be rank 1 because it's stuck in an S-cis conformation. So that will always be the case, okay? The ring-locked different color, man. Ring-locked S-trans is bad, and ring-locked S-cis is good. So ring-locked S-trans will always be rank 5, and ring-locked S-cis will always be rank 1. Now, what about the other ones? So take a look at this. This first molecule is, let's take a look. I see that it is different directions. So this is S-trans. What about the other one? Also different directions with respect to the double bond, right? So that's trans and same thing, right? So these are all S-trans. So what we want to do now is rotate them, okay? Let me show you how to rotate. First, draw the S-cis, okay? Just draw. You're always going to draw this little shape right here. So I'm going to draw that. And I want to look at the alkenes now. Single bonds can rotate from cis to trans and whatever. Alkenes cannot. So if your alkene is cis, it will stay cis. If your alkene is trans, it will stay trans. So this alkene right here, it is cis because it's same side. So I'm going to keep that over here. Doesn't matter if I choose the top or bottom. Just one of them is cis for sure. So we'll draw like this. Okay, that will be the top one. Now what about this one? This alkene, different direction. It's trans. So for this other alkene, I'll make it trans. We have a bond going up, so the other one will be going down like this. Okay, I have that. And we'll do the same for the rest of them, right? We'll make them into S-cis and see what happens. So this right here is cis, so I'll do NO2. This one is also, well, this one's trans, so I'll do like that. Big red flag, by the way. I don't know if anyone noticed. Okay, cool. So before I even rank these structures, something that I just noticed is that we have an NO2. We have an NO2. This is electron withdrawing, and it's on the diene. Dienes should have electron donating groups. They should not have withdrawing groups. So we do have a donating group right here, but we have this pretty strong withdrawing groups. That doesn't mean that it won't react. It's just going to be very, very bad reaction. It's going to be super slow. So I'm actually going to rank this as 4, just because the substituents suck on this. Okay? Now we're comparing the first and the last molecule. The only difference is the alkenes, right? They have the same substituents, they have the same number of carbons and all that. Let me show you something. This is your dienophile. When you're trying to form a bond, you're going to form a bond here, and then you're trying to form a bond here. But look, this thing is in the way. So like I'm trying to form a bond with this carbon up here, but this methyl is in the way because it's inside the binding pocket. Whereas over here, both carbons are in the way, or both carbons have something in the way. In this first molecule, only one carbon has a substituent in the way. Over here, both carbons have a substituent in the way. So this has more steric hindrance, which means that it will just react slower. So this will be rank 3, and this will be rank 2. I'm just going to add a 5th molecule, or a 6th molecule. If I had this, in the S-cis conformation, it would look like this. This is the best out of the linear ones because, look, I can easily form bonds. The methyls are out of the way. So if I had this molecule in this ranking, I would place it at rank 1.5. Now, I'll give you the shortcut. Okay, you don't have to draw the S-cis conformations. All you gotta do is look for, this is the ranking, okay? Ring locked S-cis is the best. All right. Now, of course, S-cis is better than S-trans. But if it's not ring locked, they're kind of like the same thing because you can just rotate from one to the other. So when this happens, 2 trans alkenes will be the best. 1 trans, 1 cis will be in the middle. And then 2 cis is the worst. So this is like the best. This is rank 2, rank 3, rank 4. And then rank 5 will be ring locked S trans. And once again, this little ranking thing is assuming that our substituents are like the same or similar. As you saw in this case, we had a pretty bad substituent, so it like affected the ranking. But yeah. Now you're probably wondering, if you had these two, which one would react faster? They're both S-cis. It would still be this one, because what is the issue with this? It's not ring locked, so it has an opportunity to go back to S-trans. In fact, this is the more stable conformation of it. So to keep it as S-cis and then react takes more time and effort. So it takes longer. This one cannot ever rotate into S-trans, so it's always in the correct conformation, which is why it reacts faster. All right, we are good. Next, rank by SN1 reactivity. So listen, SN1 is an OChem 1 thing. However, there's going to be many versions of the same type of question. These are essentially trying to get you to rank by carbocation stability, and they want you to consider aromaticity and anti-aromaticity. Okay? So SN1, if y'all remember, your leaving group will leave and you form a carbocation intermediate. So I'm going to get rid of this and put a carbocation right here. I'm going to get rid of this and put a carbocation right here, and so on. Quick question. I think I already brought this up. I don't know, this video is like 6 hours long, so I don't remember what I said and what I didn't say. Is resonance always stable? If I'm asking this, then the answer must be no, okay? The answer is no. Because anti-aromatics exist. So make sure you consider anti-aromaticity. Don't just look at resonance is good, okay? Let's go ahead. So what do we got here? I see that we have this molecule right here is going to be, let's do the criteria check, right? So it's fully cyclic. We don't look at this, okay? We're talking about the ring itself. The ring is fully cyclic. Everything is sp2. Everything has a double bond or it has a cation. And now we're gonna look at number of electrons. I see that we have 2, 4, and 6. Cation doesn't count. So we have 6 electrons, which means that this is aromatic. Aromatics are our best, but it's possible that we have multiple aromatics, so you have to consider other things. So I won't automatically rank this as 1, but I know that's aromatic, which is really good. Okay, what about this? Number 1, is it cyclic? Yes. Number 2, is it sp2 everywhere? Yeah. And number 3 is how many electrons? 2, 4. I have 4. So this is going to be anti-aromatic. That's not good. This thing is definitely not aromatic or anti-aromatic. It's just non-aromatic. So if you're non-aromatic, then you can easily say resonance is good. I'm just saying, like, before you classify, don't just assume resonance is good. But this is clearly not sp2 everywhere, so it's not aromatic. So resonance is good. We'll just call this a secondary allylic carbocation. And then lastly, what do we have? We have a secondary allylic again. But I have multiple resonance forms. I can go resonate with this, or I can resonate like this. So I'm going to put allylic because it's more. Now we can rank, right? We have 2 non-aromatics. We have an anti-aromatic and an aromatic. So the aromatic one will be the best because it's the most stable. So number 1, this will be rank 4. And then between the two non-aromatics, the more stable one is the one with more resonance. So it'll be this one. So this is rank 2, rank 3. Next, ranked by rhenium ion stability. So this one, you can think of it like carbocation stability, but I feel like resonating would take like a lot of time. This is easy if you know how things work. So you got to remember that first of all, more EDG equals better, but the best would be ortho para to the EDG, and it would be kind of trash if it was meta. EWG is bad, but if you had to have EWG, then you want meta, and the worst would be ortho para to the electron withdrawing group. If you do resonance, then you'll understand why this is correct, but you know, we're gonna do the shortcut by just the thing I wrote in purple, pink, whatever this color is. So let's take a look. Keep in mind, we're not looking at this specifically because we're asking, like, look, we're starting with a molecule like this, and we're trying to add the bromine, right? Br2, FeBr3. So this is like the little intermediate. We're gonna go based off of the other group, like the activating or deactivating group. We're gonna see what it is and where we're placed in relation to that. So we have an electron donating group and our bromine, okay? The bromine was placed ortho to it. That's why we have a cation over here. Misconception is that this is meta to the amine, but I mean, sure, you can say that, but that's not what we're talking about. When we're saying look at ortho meta para, we're talking about the addition of the bromine or iodine or whatever you're adding. So EDG, and we got para. That's probably going to be our best because I don't know what you can do to get something better than that unless you have more electron donating groups. What about this one? This is electron withdrawing group, and I see that the cation's here because the bromine is here. So that means meta, okay. That's pretty good for electron withdrawing group. This one right here is nothing, so nothing. Now off the bat, nothing is better than electron withdrawing group because electron withdrawing groups are deactivating. So I'll put a DA for deactivating. Nothing, it's normal. Activating. Okay, next. Look, we're bonded to the carbonyl part, so it's going to be acting electron withdrawing, and it's going to be deactivating. Our bromine was added para. Not good at all. Probably our worst one. And finally, we're bonded to the nitrogen, so that's going to be electron donating, which is activating. And our bromine was attached meta. Okay. So we have 2 electron donating, or molecules with electron donating. And then we have 2 with electron withdrawing, and we have 1 with nothing. So I know that this is rank 3 because it's in the middle. Now, electron donating, the para is the best because it's following the ortho para directing. Meta is not good, but it's still electron donating, so it's better than electron withdrawing, making this rank 2. Now for the electron withdrawing groups, meta is the best out of those, and then para is like the worst. So this will be our final ranking. Keep in mind, sigma complex. I referred to these molecules as rhenium ions, but sigma complex is another term. So if you see that, know that this is talking about this intermediate right here. Rank by rate of alcohol dehydration. So this is another instance of ranking by an ion stability, and they want you to consider aromatics. So it's saying that we're under acidic conditions. So essentially what happens, everything gets protonated and it leaves as water. So you end up with a carbocation. So we're ranking by carbocation stability of the carbon that the OH is bonded to. So we're gonna get rid of this and put a plus right here. Get rid of this, put a plus, get rid of this, put a plus, and there we go. Let's classify. This ring looks to be anti-aromatic. This ring is going to be aromatic. This is not a ring, so it's going to be non-aromatic. This is not fully conjugated, so non-aromatic, and same non-aromatic. So rank 1 for sure will be the aromatic, and rank 5 will be the anti-aromatic. Now, for the non-aromatics, just treat them like regular OChem 1 carbocations, where you rank by resonance and positioning, right? Ba3, 2, 1 methyl. So this right here is a primary allylic. This is a secondary allylic, and this is just a secondary. So this one right here has no resonance, so it's going to be the worst out of the 3 non-aromatics, so we'll rank this as 4. Now, these 2 non-aromatics, don't be quick to say that this is the better one because it's secondary allylic versus primary allylic. You don't look at the positioning yet. We want to look at number of resonance forms. This carbon has resonance with 2 double bonds. If you don't see that, look at this. You resonate over here, you're going to get a plus right here. Then you can resonate again. Right, so you have more resonance forms for the primary allylic one, whereas this one only has 1 resonance form, or 2 technically. So the better one will be this because it's allylic. So this is going to be what? Rank 2 and rank 3. So rank 1 is aromatic. If you're comparing 2 aromatic things, just look at which has, actually, don't worry about this. There's so many things to consider. It kind of depends on what you're looking at. But rank 1 is aromatic, then rank 2 is going to be non-aromatic. And if you're comparing these, you're going to look at which has more resonance. That's the first thing you look at. Then you want to look at positioning, if your resonance is the same. Okay, then the worst would be anti-aromatic. Rank by acidity. Once again, another example of ranking by an ion and considering aromaticity and stuff. But instead of doing a cation, we're doing an anion. So first of all, acidity is referring to stability of a conjugate base. We look at conjugate base because acids want to lose a proton. And if an acid loses a proton and it ends up being a very stable conjugate base, then that means the acid is really acidic. It really wants to get rid of it so that it can become a stable version of itself. So we're going to deprotonate every molecule at the best position and put an anion there. And we're going to rank by anion stability, essentially. So this nitrogen will lose the proton, and it will lose its positive charge and become neutral. Because it was plus, so you lost the plus, making it neutral. This one, negative right here. And over here, we're going to put a negative right here. Let's classify. This time we have an aromatic molecule right here because there's the lone pair to consider. So it's 6 pi electrons. This one's going to be anti-aromatic. This is going to be aromatic because we have a lone pair that can resonate. So there's no negative charge, but it's still a lone pair. So it's going to be aromatic. This one, we have sp3 over here, so it's just non-aromatic. And finally, we have this ring itself, which is aromatic. So as you can see, we have 3 aromatic molecules. This is why I didn't finish what I was saying up here because I was just going to show y'all. We're going to have to figure out how to rank the different aromatic ones. That's why I say don't be quick to put aromatic as the best or anti-aromatic as the worst, because if you have multiple, then you got to do stuff. But this time we have 1 anti-aromatic, so this is rank 5, and the non-aromatic will be rank 4 just because we're left with just aromatics. So the first thing you can see is that this molecule right here has no charge. The other 2 aromatics have a charge. So it's better to just not have a charge than to have a charge. This is not always the case, but for y'all, you can think of it as always the case. It's better to have no charge than to have a charge because there's less stuff you have to worry about. And this is aromatic, right? So it's good. It's rank 1. Now, these 2, I see that we have this cyclopentadiene type structure. The only difference, right? They're both aromatic. They're both the same structure. The only difference is that this molecule has a lot of electron donating groups on it. This one has nothing. So we know that electron donating groups is bad for negative charges, which means that this one is a little bit less stable than the first molecule. So our answer is going to be that this is rank 2 and this is rank 3. Now I have to clarify, we only looked at the fact that this had no charge because it's aromatic. If I gave you a molecule that looked like this would not be in the top 3. This would be like around the non-aromatic one. Okay? Yes, this is neutral, but it is not aromatic. So you don't look at the neutral stuff. You look at aromatic first. If everything's aromatic, then you can look at being neutral or whatever charges you have. So just keep that in mind. All right, next. We got nucleophilic aromatic substitution. We're ranking by. So this one is different from EAS, right? EAS, we wanted more electron donating groups because withdrawing groups were bad. However, for nucleophilic aromatic substitution, you want more EWGs because it's like the opposite. You want more electron withdrawing groups so that your benzene can act as a electrophile. Another thing to consider is leaving group. So your leaving group order is going to be very different than what you expect. Fluorine is better than chlorine, is better than bromine, is better than iodine. This is odd because, first of all, we know from SN2 that fluorine is not even a leaving group, and the ranking is usually flipped. Iodine is the best. This is not an SN2 or SN1 mechanism, okay? This is a very different mechanism, and what you look at is electronegativity. You don't look at polarizability. You look at electronegativity. Therefore, fluorine will be the best. So we have a couple of things to consider, okay? Let's take a look at what we have. One more thing, actually. The electron withdrawing groups, if you have them, you want them to be ortho, para to leaving group. Meta is bad. I don't think it will work. So let's see what we have. We have one electron donating group, and it's para. One electron donating group, and it's para to the leaving group, right? I have two electron donating groups, and they're both ortho or para, so that's good. Over here, I have I have two electron. Oh my god, I'm so cooked. I meant withdrawing group, sorry. Withdrawing group. Okay. And both of these are meta. And lastly, we have two electron withdrawing groups, and they're ortho para. Okay. So right off the bat, this is going to be the worst, right? I said we want more electron withdrawing groups, but we want them to be ortho para. These are both meta, so that's not going to help us, right? We went over the mechanism earlier. That's not going to help us at all. Therefore, this is going to be rank 5. Then we can look at the two electron withdrawing groups because both of these have orthopara. So the distinguishing factor here is that this one has fluorine, this has chlorine. Fluorine is a better leaving group than chlorine, so this will be rank 1 and this will be rank 2. Then we're left with the one electron withdrawing groups, which are both para. Same thing, the distinguishing factor is the leaving group, bromine versus chlorine. Chlorine is higher up on the periodic table, so it's more electronegative. So this will be next in line, and this will be rank 4. So I'll mention again, M is bad. We can scrap EAS. We're just looking at NAS, right? Rank by nitrogen basicity. Talked about this earlier, but this is another question. So our lone pairs, we're going to look at the orbitals that they're placed in. This nitrogen already has a double bond, so the lone pair will just be in the sp2 orbital. This nitrogen is allylic to the benzene double bond, so this lone pair will be in the p orbital. This is going to be sp3. This is like the same thing as the second example, so it's going to be p, but we have this suspicious group, and this is going to be sp. So remember, sp3 is better than sp2, is better than sp, is better than p. So rank 1, our most basic would be this one. And what else do we have? Rank 2 is sp2, rank 3 is sp. So the only difference between the two p's, they're both part of this whole like benzene aromatic system, so we don't have to look at that. The only difference is the presence of this NO2. So the way you can think about it is if I gained a hydrogen, we would have NH3 plus. NH3 plus, okay? This is an electron withdrawing group. It's withdrawing electron density from something that has no electron density. So that's not really good. It's like destabilizing. So we'll just say that this molecule is better. No, what am I saying? We'll say this one, I'm actually so cooked. This is better than this one, right? This one really doesn't want to gain a bond to hydrogen, because if it does, not only will it be difficult to do because of the resonance stabilization, it's going to be unstable from this NO2. So we'd rank it like this. Now we're going to do some synthesis and reaction practice. I pulled out just like some random questions that, I don't know, I thought were like low-key difficult, or like maybe people have questions on. But obviously I can't do too much, otherwise this video will be like 8 hours long. So let's go ahead and start and speed run. Okay, this is not a naphthalene. Okay, naphthalene is when you have two benzenes that are like together, like literally like the same molecule. This one has a bond between two benzenes. So this is just like two benzenes, it's not a naphthalene. So which means that you don't have to follow that rule I was telling you. Instead, just think of it as though you're figuring out the most activated of the two rings. The most activated one is going to be this one, because we have the OCH3, which is electron donating, whereas the NO2 is electron withdrawing. It's deactivating. Okay, so this is deactivating and this is activating. Now, this is an ortho-para director, and this is an electrophilic aromatic substitution reaction. So we don't have a para position present, so we're going to use the ortho positions. You can do either of them because it doesn't matter. They're the same thing, it's symmetrical. So that's going to be our answer. We're going to attach like this. So you have our OCH3 here, and what are we adding? The NO2. So the NO2, you can just put it right here. So that's our answer. Next, this is interesting. That's why I included it. This is Diels-Alder. Okay, I know it doesn't say heat or anything, but you don't need that. Okay, you do need heat, but they don't have to mention it to you. All you gotta notice is this diene and then the dienophile, and you know that we're doing some Diels-Alder. Okay, so I see that my substituent is on the internal carbon, which means it's going to be a 1,4 product. If you don't know what that means, go back to the part where I talk about Diels-Alder. We're gonna have a 1,4 product. So I'm gonna draw my cyclohexene. And I'll put this is tips, by the way. This is O tips. This is what we talked about earlier, the protecting group. And then our NO2 is going to be the 4 position, like that. And we're going to put it on a dash because it has a pi system. Okay, so we did this. Okay, this was step 1. Now step 2 is TBAF, which gets rid of the protecting group. So TBAF is deprotecting, which means that we're going to go back to an alcohol. Now, if you put this as your answer, I think it's fine, because I don't know if they expect you to do this next part, but technically what happens is a tautomerization. What do you have? You have an enol. And if you remember anything, enol tautomerizes into keto, which is the more stable version of it. So technically, your final product would actually be this. Don't trip too much about this, though. So that's your answer. All right, next. NaNH2. So this is a nucleophile and looks like an NAS reaction because, I don't know, it just looks like it. So I have NO2, which is going to be our electron withdrawing group, which helps with NAS. We're going to be attacking the fluorine for 2 reasons. Number 1, fluorine is the better leaving group. But secondly, the NO2 is actually ortho to the fluorine. If we look at the chlorine, the NO2 is meta to it. And remember, we need to be ortho or para. So that means that we're going to be replacing the fluorine. So just typical to keep it simple, that's what happens. But obviously that's not the legit mechanism, but nobody cares, so we're going to do that. So we're going to add our NH2 here. And we have our NO2. We'll keep the chlorine. So that is our answer. Right? It's one equivalent. Even if you had like multiple, I don't think this would react because your NO2 is meta. All right, HNO3. So this one right here, we have an ester and we have two benzenes. I think by now you should know how to approach this, but this is going to be the activated benzene and this will be deactivated because the left side is attached to the carbonyl, whereas the right side is attached to the oxygen. So this is the activated one, right? And we're doing an EAS again. So we're going to add to the ortho or para position. We do have a para position available, so our answer will be that. So like right here, NO2. This one is weird, but don't panic, right? You see a bromine and you see FeBr3. They didn't, like normally they give you something, right? Like that, or they'll just say like Br2, FeBr3, and whatever. They didn't give it to you. They just gave you the catalyst, and the Br is present here. So this is going to be an intramolecular reaction or intramolecular Friedel-Crafts alkylation. So essentially, this bromine is going to leave, and you form a carbocation right here. But remember that when it comes to these carbocations, they can rearrange, and they will always rearrange if you have a better position available. So it's actually going to move down here. Okay? One, two, three, four. Now, it doesn't matter if you attach to this one or this one because they're going to be the same. They're both meta to this electron withdrawing deactivating group. So you can just do either of them, doesn't matter. By the way, if you're wondering, is this 2 deactivated? I guess, but you still have this methyl, this alkyl group attached, so it kind of mitigates that effect. So the answer is not no reaction. You'll still react. Okay, so we have, erase this, I misnumbered. So carbons 1, 2, 3, and 4. So 3 is going to bond to, we'll just choose that one, okay? And 4 will be like a substituent off of that. So we're going to go ahead and draw our benzene. And we're going to add our, that. And now look, carbon 1, 2, 3, like that. Horrible drawing. So look, carbon 1, 2, 3. Right? 3 bonded to that top carbon. And we're not done because carbon 3 also has a methyl. So that would be our answer. So don't forget the rearrangement. So that is step 1. Step 2 is going to be with SnHCl. This is like basically Clemenson, which is going to reduce your benzoic carbonyls. So your answer, your final answer would be this. Just chop that off. That's your final answer. All right, next. What do we have here? So this right here, I actually brought it up because okay, I don't have the picture on me, but you're going to see IR and NMR on your exam, okay? It's going to be like this. A reacts with something to get B, B reacts with something to get C, and they'll give you some reagent. This was one step, right? This was like A to B. This is A, and they're figuring out what B is, okay? They give you this, they say a bunch of words at the top, and then they'll give you the IR, NMR, and all that stuff. And everyone starts panicking, like, what do I do? And then they fail their exam and they cry, and then they, retake OChem. It's not like really hard. So the NMR and IR is kind of there to confirm your answer. You don't have to figure out the answer from the NMR. It's there just to confirm, right? Like making sure you placed in the para position compared to oro or ortho or something like that. But you can figure out the answer just from the reaction itself. Now, I do get it. This reaction looks suspicious. Like, it looks a little bit different because normally when we see AlCO3, we have a chlorine present. Over here, I see that we don't have any such thing. But if you understand how these reactions work, if you try to apply the same logic to something that looks a little different, then it should work, right? This is not a different type of reaction. It's the same thing. This is called an anhydride, by the way, or a cyclic anhydride. It's like a carboxylic acid derivative, but you're going to treat it the same way, right? So essentially, I would think of it as though this was like the chlorine, and just let's choose this side, okay? Pretend that this side doesn't exist. What happens when you have AlCO3? This chlorine leaves and you put a plus right there. So in the same way, I want you to think of it like that, but this time you have an O. So this O will break off and you'll have a plus right here. So you can look at it like this. Like that, right? We'll just make this an OH because of protonation. Technically it's an O minus, but it doesn't matter. Now, this is our E plus. This is our electrophile. And so our benzene will attach it like that. So we're going to draw our benzene. Yo, it's kind of crazy. I started this video at like 3 a.m. and now it's 5 p.m. My God. Anyways, let's add this. Let's number 1, 2, 3, 4. So bond to carbon 1, 2, 3, 4. Carbon 1 had that. Carbon 4 has this carboxylic acid, and that looks good. So that is it for step 1. Then step 2, H2PT. Remember, this is only going to affect our benzylic acyl group. So we're going to end up with, also it's not strong enough to reduce carboxylic acids. This is our final product. And of course, right, you have the NMR and whatever, and they'll give you the formula, C10 something something. It doesn't matter. You can like figure it out on your own. I'm going to jump in and mention one thing because I just forgot while I was editing. This is a question that might show up, and you should be able to tell what it is because you have a diene here and a dienophile, and you have heat, right? This is going to be Diels-Alder, but an intramolecular version of it. So what I would do is the same as always, where you're going to number 1, 2, 3, 4, and then we'll just number fully, right? 6, 7, 8, and 9. We'll stop there. Okay, we'll go from the diene to the dienophile. Now, we're going to draw our cyclohexene ring. And we'll number this 1, 2, 3, and 4. But now we have to see, does 4 bond to 8 or does it bond to 9? The way I would look at it is carbon 1 has just a CH3. Carbon 4 has this big long chain. Of course, it ends up into like an NO2, but it's still a super long chain. It's more carbons than carbon 1 has. So I would do the 1, 2 positioning based off of carbon 4. So carbon 4 and 8 are going to be bonded to each other, and 1 will be bonded to 9. So carbon 8 will be here and 9 will be there. By the way, if you do it the other way, you'll notice that you won't even be able to figure out the product because it just won't make sense. I don't know if I can explain that, but yeah, you know what? I can explain it. Do you see how carbon 4 and 8 are linked by 5, 6, and 7? That means that you have to have carbon 4 and 8 bonded to each other, because essentially what's going to happen is you're going to draw carbon 5, 6, and 7. Okay? So 5, 6, and 7. If you try to bond 4 to 9, so you did it like this, you got 8 up here, you have to link 4 to 8. But like, how do you do that? It doesn't make any sense. So that's not the way you can like confirm. So 4 is bonded to 8, and this is 9. Okay, so carbon 4 is going to be bonded to carbon 8. So once again, 5, 6, and 7. So you have like a cyclopentane type thing here. And you can indicate stereochemistry. I don't really think it's necessary. If you did, it would be on a wedge. But I've seen people like put this without the stereochemistry and they got it correct. Because usually with rings we don't indicate stereochemistry, but technically it would be on a wedge. Okay. Now carbon 1, its substituent is going outwards, right? I didn't make this S cis, but if you did, it would be going outwards, like outside the binding pocket, because alkene itself is trans. So carbon 1, its methyl, is going to be on a dash. And then we have carbon 8. Carbon 8 has an NO2, endarule, dash. And then this ethyl is going to be cis to the NO2, so we're going to put this on a dash as well. And yeah, that's going to be our answer. Now we're going to do synthesis, okay? And specifically just like benzene synthesis stuff, like Diels-Alder. I already did it, right? So we don't have to do that. So I don't have the picture on me, but if you look at any old exam, you're going to see something like this, where they'll give you a starting material and the ending material. And they're going to give you a word bank on top. They're going to give you like reagent A, B, C, D, all the way to like, I don't know, M or something. And each of those will be reactions that you know, like the aromatic reagents. And what you have to do is figure out what order to use them. Because remember, right, some things want things to be meta, other things want things to be ortho. Some things deactivate so much to the point where you can't even react. So that is the quote-unquote difficult part, just knowing the order. But to be honest, it is so easy because they give you a word bank, and like if you know the basic rules, like it's so easy. But I'm not going to do it with the word bank because I'm just like that. Also, I don't know where the word bank is. So we're going to like logic this out, okay? So let's see what we got here. I see that we have this NH2, and I have an alkyl that is ortho to it, or para. So initially I was thinking that maybe, you know what, just go ahead and draw out your thoughts, right? I was thinking maybe at first I can add an NH2 and then add this on, but the problem is I can't add the bromine, because if I did add the bromine, it would be over here, or you know, it wouldn't be based off of the NH2. Sorry, what am I saying, bro? It wouldn't be based off of this. It would be based off the NH2. So that wouldn't really work. Another thing I can think, maybe I had NO2. Right? Because you have to go from NO2 to NH2 anyways. So maybe I had NO2 and then I added a bromine. But then the issue here is like, where would this go? It wouldn't go here because this is ortho-para-directing, so it would probably go up there. Also, this NO2 is meta-directing, so maybe it would go here, right? But it's not going to go where we want it to go. So that doesn't help. So now my third thought is, what if we start with this? I think that's going to work. So we're going to do that, okay? There's no other option, so I'm just going to start with that. So remember, we're trying to add a straight chain that is more than 2 carbons long. So we can't do this reaction right here where it's Cl, AlCl3, because remember, you're going to get this as your intermediate, not that. So we have to do acylation. So we're going to make a 3-carbon molecule that has the acid chloride, and then we'll do that. And we'll get that. Now I'm going to go ahead and just reduce this because I'm like anticipating that I'm going to get this added on as an NO2, and then I'll add this. Just follow along, okay? So we got this. Next step would be ZnHCl, Clemmensen reduction. So we got that. Now I'm going to add the NO2. So HNO3, H2SO4. And it's going to be ortho or para. I have both options available, so just go with the para. So we got NO2. Okay. Do I want to make this into an NH2, or do I want to add my bromine? Think about it. If we do make that into NH2, then our bromine would be either here or here because the NH2 is stronger. And we want the bromine to be ortho to our alkyl group. So I'm going to actually leave it as NO2 for now, because in this case, I have only ortho positions available for the alkyl, and these blue squares are meta to the NO2, which is perfect, right? Satisfies both. So I'm going to add my bromine like that. It's got Br2, FeBr3. And then finally, I can go here if I use ZnHCl or like ZnHgHCl. That will reduce the NO2. Remember, do not use Wolff-Kishner. This does not work for the NO2. It does work for the acyl, but not for the NO2. So that would be our answer. Okay, we'll do, what do we have? 2 more? Okay, so 2 more, then we'll finally be done. This one seems light. Honestly, I can take it either way. So actually, let me show you both ways. I'll tell you what the better method is, but the first method would be to add the... Never mind, I'm stupid. Okay, so we're going to go ahead and add this, or we can add this, but I think we're going to go ahead with the NO2. So we'll add the NO2 first. I'm not going to lie, I don't know how to explain what I'm thinking. Here, let me tell you, right? You cannot add an OCH3 off the bat, right? You can't do electrophilic aromatic substitution. You would have to do nucleophilic aromatic substitution, and there would have to be like a fluorine here or something like that. And on top of that, you would have to have an electron withdrawing group. This is electron donating, but it came from an NO2, which is electron withdrawing, and it is placed para to this thing. So what I'm like anticipating is that there must have been something like this where you had NO2, and we'll just go with chlorine here. I think something like this happened, and then we reacted with NaOCH3 to do an NaS reaction, and then that would give us this, and then the last step would be to reduce the NO2 with the ZnHCl. That's what I'm thinking. It makes sense, right? So I guess in this case I worked backwards, so let's just keep working backwards-ish. Or we'll go forwards now. We're going to add the NO2 at first, so the HNO3, H2SO4. So we got NO2, and then we're going to add the chlorine, so Cl2, AlCl3. Pretty deactivated ring, but that's only an issue for electrophilic aromatic substitution. This is perfect. This is perfect for, I mean, we just made this molecule, by the way. This is perfect for NaS because it's electron deficient. So let me make sure I didn't trip up. Yeah, it looks good. All right. Last one will be this one right here. So carboxylic acid, the only way I can think to add a carboxylic acid to a benzene is by doing KMNO4, and then that would do the cleavage and oxidation thing. So yeah, something like that. I think I'm gonna go ahead and work forwards this time. I'm gonna just add, you can add anything, to be honest. Like you can add any carbon as long as it has one hydrogen present on the carbon bonded to the benzene. So I'll just do this, ClAlCl3. That will give us an isopropyl, which doesn't matter because I still have an H right here. Then I'm going to do potassium permanganate. No, I'm not going to do that. I'm going to add in my NO2, right? So I'm going to do HNO3, H2SO4. And I'm doing this on purpose because I want my NO2 to be para. If I made my carboxylic acid first, that would be deactivating, right? And my NO2 would not be para, it would be meta. So I purposely left the alkyl as it is so that I have this NO2 in the right position. Then the last step is to use KMNO4. KMNO4 will just chop this off, and make a carboxylic acid. And that is my answer. Okay, we are officially done with everything. I am so paranoid I forgot something, but this is crazy. I really thought this was going to be a super short video, like 2.5 hours, but there was so much to talk about that it just ended up being this long. Yeah, if you have any questions, drop them below. I'll probably be in the peer tutoring lab like all of Wednesday, so you can like find me and harass me with questions. And like if I say anything wrong, just let me know. But I'm pretty sure, like, dude, when the videos are super long, there's always a chance that I just like say the wrong thing and don't even realize. But I think for the most part, everything should be good. Also, like, yeah, one last time, I always say this every time there's reactions to learn, but I go over most of the reactions, especially like the ones that you need to know. But it is possible that I skipped over some minor reactions. So if you want, just go look over your notes and see. You can also get a feel for if something is necessary to know or not by looking at old practice exams and old quizzes and stuff. If you keep seeing a reaction show up, then you know you should probably know it. If you don't ever see it, then maybe not. But yeah, good luck, and I'll see y'all next time for our final video ever for organic chemistry with the final exam review. Peace out, everyone.